Buenos días a todos.
Hola, buenos días.
¿Cómo están?
Muy bien, aquí ya esperando
¿Listos
a
para...?
que sea la hora.
Muy bien. Seguimos entonces por aquí. Saludos.
Gracias.
Hola, hola a todos, buenos días. Hello, everyone.
Hola, hola.
I think I will now speak in English since Sophie is now connected and the event is programmed to be in English. So I welcome you and thank you for being in the workshop. So we are on time for the very first talk, who is from all the speakers are Fabio Miranda Perea, Jimena Estrada Zabaleta, and Lourdes del Carmen González Huesca. And the talk is titled Feature Style Model Necessity as a Substructural Sequence Style. So now I will ask the speakers if they want to stream the video or they want to give the talk now.
Hi, now I'm going to give the talk live.
Good.
So I will start sharing my screen.
Go ahead, thank you.
So, okay, thank you, Everardo, and thank everyone from being here. I'm going to present our work. Everardo just said the title, so I just start. So, as the title says, we are interested in Fitch-style proof systems. And as we know, Fitch in 1952 reintroduces this kind of proof systems, which the main feature is that the proofs are developed in a diagrammatic way, and also that the use of temporal assumptions give us a style of subordinate proofs which are marked or which are given by these temporal assumptions. So these diagrammatic systems are very visual, are very easy to develop a proof. And also the diagram is defined and is intended to be used as mark or to track all the subordinate proofs. Later, Borgius in 1998 gives a Fitch-style system to be used using a modal logic. This system also has these visual aids, these diagrammatic marks, to use these temporal assumptions and also to incorporate the modal assumptions that can be used during the proof. These temporal assumptions are named or are denoted as strict subordinate proofs. And the main idea of this is that we can follow the semantics of modal logics, this Kripke semantic or this Kripke interpretation, that we can change the words to study different propositions. So these strict subordinate proofs represent this changing or this traveling to arbitrary words. And this system also has two kinds of rules. The first one are the importation rules that denote some kind of reiteration rules in the way Fitch defined some these reiteration rules. And the other kind are the ones that are named exportation rules. These exportation rules allow us to close the strict subordinate proofs. That means if we start or we use a temporal model assumption, these start a strict subordinate proof, and then with the exportation rules, we can close this the diagram or the subdiagram started with this temporal model assumption, and then given us the idea of returning to the actual current world that started the proof. Which are the rules of this system? Well, we have these importation and exportation rules. You can see here the diagrams. And the main feature of this system, this Fitch style system for modal logics, is the use of a special symbol that is called the lock symbol. This symbol allows us to define this strict subordinate proof, as we can see in the four modal rules. Here is our running example. We want to prove or to derive a box that box A implies box B from the hypothesis box A implies box implies box B. Here we have the proof, and we don't have another connectives, but just the implication and the modal necessity, the box modal necessity. So here is a proof. Each step in the diagram is justified, or it has the name of the rule applied to obtain the formula in such step. And also it's accompanied by the number of the propositions or the model or the formulas that are used to use this and the rule, to apply the rule. So this is the system. We have diagrams, we have nice proofs. We have two aids, two visual aids, the big boxes or the lines that encloses the strict or the subordinate proofs, and also the lock symbol to say that we have started strict subordinate proofs. So this kind of diagrammatic way to develop proofs is captured by a strict or a mathematical definition given by this such a proof scheme or proof figure. This proof figure has three components in order to define strictly or closely these diagrammatic proofs. The first one is the interval that denotes the total steps in the proof. Then we have a function f to map each number in the proof, each step in the proof with a proposition or with a formula. And finally, we add a third component that is a collection of intervals to define the beginning and the end of a subordinate proof, either normal or ordinary strict subordinate proof or strict subordinate proof. So this collection of intervals is decomposed in two collections. The first one, the O collection, to define the ordinary intervals. This means the subordinate proofs, as we know in the Fitch style kind of proofs. And also the other collection that is the M collection for modal intervals. These intervals will denote the strict subordinate proofs. That means the ones that started with a lock and are closed with the application of the correct rule. This formal definition captures the diagrammatic style of the Fitch styles proofs and also keep the visual intuition about these starting and ending subordinate proofs. To complete this formalization, we give a function that helps us to keep track of these subordinate proofs. We add the degree functions, which are just the mapping between the number of steps and the number of active subordinate proofs. So we have to keep track of the open subordinate proofs, the ordinary subordinate proofs, and also the modal or the strict subordinate proofs. This definition also helps us to keep track of all the steps in the proof, all the subordinate proofs, either by the ones that are ordinary or the modal intervals. So together with these definitions, we can adapt our examples or our proofs by adding the degree functions for each proof step. For instance, here, the step number 5, you can see that it is inside two strict subordinate proofs that are marked by these two logs. And also it is inside another subordinate proof, that started in the step number 1. So the degree of the step or the formula number 5 is 2, 1, as it is inside both two strict subordinate proofs and one subordinate proof. We can see these degrees changing as each step could be the application of a rule that closes a subordinate proof or that opens a subordinate proof. So, for instance, the step number 8 as is the application of the T-exportation rule, closes or finishes the strict subordinate proof that started in step number 5, and we can see that the degree has decreased in just one number, and we can interpret or read this pair 1, 1 as the step number 8. This formula, box B, is just in a strict subordinate proof, and also inside a strict in a subordinate proof. So also with this kind of annotations to extend the proofs in this Fitch style linear schema, we need to formalize the notion of unfinished proof. That means, suppose that we are just looking at the proofs of the part of the proof that started from 1 and is actual in the step number 6. We have to adapt the notion of proof to the one that can express that a proof is not finished, and also that the boxes or the subordinate proofs are not closed. So we give also a definition of pseudo-proof to establish these notions of open or unfinished proof, which is the central idea that we will use later in other results in this article. Also, we give the definition of a proof, of a complete proof. So we can give the conditions of a proof figure in order to say that any proof figure or a given proof figure is a complete proof of a statement. So until here, we have just given all the ingredients for a formalization of the Fitch-style proofs. And all these ingredients are useful for a mechanization. This means that we can implement this in a proof assistant. So we have this relation between the active or the context with the hypothesis and the assumptions of a proof. And this relation between this context and the actual proposition that is being proved is internalized by what we know is a sequent, this relation. So we can forget the diagrams, as all the formulas that appear in the context are available at each step in the proof. So what about the subordinate proofs? The ordinary subordinate proofs are modeled or are given by this initial rule or the hypothesis rule that says that the last formula in the context is allowed to be concluded in the rule. About the subordinate proofs to close a box or a subordinate proof, we use this introduction rule of the implication, as the last formula is going to be discharged and construct the implication with the consequent of the other sequent. So this is good. We know that this is the case or the correspondence between Fitch-style proofs and sequent-style proofs. And the main idea for this correspondence is that the elements or the formulas belonging to the context need to respect some order. This order is imposed by all the steps in the proof and also by the subordinate proofs that could be started in the proof. So in order to implement this, we need to consider a data type that is able or that is capable to maintain this order in the context. So we choose the least data type. So this is just a low-level observation. So far we have given this or the setup of this correspondence between Fitch-style and sequent calculus. What about the rules that model these modal logics? So we have importation and exportation rules. For instance, we have these two rules that are related to the K axiom or the K scheme in modal logic S4. And Clostone in 2018, he gave a proposition or an article that stated modal lambda calculus that he says captures the Fitch-style for modal logics. Nevertheless, he didn't give a proof, but he explains that the rules that he gives in the system NS4 are equivalent or model the same ideas that the diagrammatic rules are with this log and all the combinations of formulas and boxes. here I put these two rules. The K exportation rules, we can see that corresponds directly with the name should rule. That means that if we have a lock in the context, or we have started a strict subordinate proof, we can close this subordinate proof by boxing the last formula in this subproof. So we can see that the correspondence is clear, but in the other side, the K importation rule is not directly correspondent with the open rule. In fact, this open rule is very general, as we can see here, that the conclusion of the rule involves an entirely new context or subcontext gamma prime that can be used to derive A from gamma and box A. So this rule is not entirely modeling this diagrammatic rule, the K implication rule. So we started to study this system. We came with this question: what is a sequence style system for Fitch style modal logic? We have the correspondence for implications, and we are not very happy with this proposal of Closton. What is the main idea? We need to model these two kinds of subordinate proofs, the ordinary subordinate proofs and the strict subordinate proofs that are marked with the log symbol. These strict subordinate proofs are not triggered by a formula. This is what I have said. They are triggered by the open log symbol in order to start or to move to another world in this Kripke semantic idea of modal proofs. So the diagram, the context, need to add an additional element that will be a formal element, the log symbol. So for instance, if we have a context of this form, this context can be read or can be interpreted as there are four subordinate proofs that are active or that are not closed. The first two are, or the closer are the B and C ordinary subordinate proofs. Then there is a strict subordinate proof denoted by this log symbol, and then there is another subordinate proof that is ordinary. So we need to incorporate this formal element in the definitions we give, and also in the rules for this sequence style system. And we need to keep this order in the context, as the presence of the log symbol generates a substructural logic. This is what I'm going to explain now. So this is the rules of our system. These are the rules of our system. We have the implications rule, the modus ponens, that in particular is share the same context for the premises in this rule, and the implication just mark, as I described, the discharging of the last formula in the context. The hypothesis rule is stated in a more general way. We can conclude any formula in the context, but with the restriction that this formula is inside a strict subordinate proof. And this is defined with this lateral or this additional consideration of the rule, as all the elements in the right side of the context, or in the last formulas or elements in context gamma prime, are not the log symbol. So this will ensure us that we can use a formula that is inside a strict subordinate proof, and this formula, we can imagine that this formula is available in another world different from the one that started the proof. The other 4 rules are the rules that correspond to the exportation and importation diagrammatic rules that are given in the Fitch style system. And these 4 rules correspond directly with these formulas or these diagrammatic schemes in the Fitch style. So let's see our running example. We have this derivation. We want to derive this. So we have one hypothesis and the conclusion. This is the linear proof. And as we see, it's entirely in the sequent style form. Each step is marked or is labeled with the rule, the use rule, and also the other steps that are needed to apply the rule. And for instance, we can see here the step number 7. The step number 7 is the result of applying the modus ponens rule of steps 5 and 6. But the interesting point here is that the lecture or the way we can read or interpret the context in each step or in each sequence. So we can see here that step number 7 concludes box B, but this box B is inside one strict subordinate proof, one ordinary subordinate proof, another strict subordinate proof, while using the hypothesis given to perform this proof. Step number 8 is the application of the de-exportation rule. This means that we will close a strict subordinate proof, and we can see here that the lock has disappeared as it's marked to be closing this subordinate proof. So these sequences are clean, the proofs are nice. And what we want to say now is that we have this, the properties of this system. This system is substructural as the rules that are structural are not available in this system, or not in the general form. First of all, we need to see that the modus ponens that have different contexts is not a sound rule in this system. We don't have this rule. We have the modus ponens with the sharing context, so we are okay with that. And the other structural rules, as I said, they are not available. So weakening, exchange, and contraction are sound with respect the formulas, either ordinary or propositional or modal formulas, but not in general, thanks or because this formal element that we added in the context that is a lock symbol. So for instance, weakening, we can just not apply a weakening in the presence of a lock symbol. We cannot also exchange 2 elements in the contents when one of these elements is a lock symbols, because this will mean that we change the order in which a strict subordinate proof started. So we cannot exchange for free these elements. And contraction is not even available, or is not an admissible rule, because we cannot contract the same formula if there is a lock symbol in the middle of the same formula. This means that we cannot forget that we are in another world that was marked, or that was started by a strict subordinate proof marked with the log symbol. This, if we use these rules in this general formulation, we will prove this, the formula A implies box B, that it's an unsound formula, and we don't want to have an unsound system. However, we have the four structural rules, but in a restricted way. We can just weak the context or adapt it with another gamma prime or with other formulas, only if the conclusion is a box. Opening is available when we are inside, or we are using or opening a box formula. We can replace a strict subordinate proof by another proof. And the only thing that we are allowed to contract is two logs. That this means that we have opened two strict subordinate proofs, but we can just open one and contract these elements. What about the proof of the equivalence between the Fitch-style system, this diagrammatic system with these rules, and the sequent style system? This equivalence, we can prove the equivalence between the elements or the derivations in these two systems by defining the equivalence between a pseudo proof in the Fitch-style system and a sequent in the system NS4. And this limitation, or this way of stating this equivalence, is given by the use of the hypothesis rule. This rule is absent in the Fitch-style system, whereas in the NS4 system, the sequence-style system is available. So we need to adapt this proof of equivalence to say that a pseudo proof is equivalent with a derivation in the system NS4. Moreover, in NS4, due to the definition of sequence, we have several induction principles. We need to prove stuff by structural induction of the sequence. Also, we can use strong induction by means of these functions that define the Fitch-style proofs. And also we can do induction over the context. Even that, these induction principles are very useful in when mechanizing or doing the proofs. And the main ideas of this mechanization will be that the contexts need to be managed in a very detailed and strict way, as they need to keep the order of the formulas inside the contexts. So the equivalence is stated with these two statements. The equivalence or the simulation of a pseudo proof in the Fitch style that give us a derivation in the sequence style, and the other side. So to conclude, we have presented two systems that are for the modal logic S4, just for the necessity fragment. The system F, which models Fitch-style proofs by means of a definition of formal proof as a mathematical structure, as a strict and rigorous mathematical structure. And the other side, the sequence-style system, and S4 that really captures the Fitch-style diagrams, and also this idea of subordinate proofs. We want to mechanize these results in a proof assistant, mainly in the COG proof assistant. So this is why all these formalizations and all these all the detail of the definitions are needed. And also we want to define proof-served procedures, but this future work is challenging due to the substructural nature of this sequence style system. So this is all. Thank you so much. Gracias. And I will be here for your questions.
Okay, Lourdes. Thank you very much for your presentation. And we have some minutes for questions or comments. Okay, in the meantime, maybe somebody want to formulate the question. I would like to ask something and to comment a bit. So first of all, I congratulate you for the work. Second, as far as I know, some of the results in this that you presented are part of or in the context of a master thesis from by Jimena.
From Jimena. Mm-hmm.
So I am very happy for that, because some of the aims of this workshop is to involve students, and that's why I'm very happy for that. And second, I would like to ask you some of the context or some of the motivation for this work. So now that you have you have proved a nice result, saying that this feature style system is equivalent to the model lambda calculus. But what's your motivation? Can you tell us a bit more about this context, please?
Yes, with Fabio, we have a project that the main subject is studying modal logics for different applications in computer science. And we have some works about S4, the modal necessity fragment of S4. And we start, also Jimena started working with this system, the Fitch style system. And the work of Closton, he departs from the idea of formalizing the stuff, but he works with the definition under the categorical area, or the categorical part of these systems, by formalizing or giving all the definitions in category theory. But we keep the idea of using these logics for applications, for some readings, or use this modal logic for computational interpretations. So we are interested also in filling the gap between this diagrammatic way of doing proofs, and also the reasonings that are behind these diagrammatic proofs, and to close these proofs, or I don't know how to say it, to study them inside proof assistant, or how we can help or get the help of the proof assistants to complete this interaction between the two sides. The mathematical side, let's say, by the ordinary way of doing proofs, and also the way some people use the proof assistants in order to reason and to develop proofs. So this work is not finished. We have many things to do, and this is the motivation of studying these Fitch style systems, and the equivalence for having a formalization and a mechanization proof assistant. I don't know if Fabio want to add something, but this is the main motivation.
Okay.
Only maybe that.
So there's a question in the chat.
Fabio is talking, but I don't hear him.
Can you hear me?
Hay una pregunta en el chat, Everardo.
Sí.
Martín
I will
Castro.
read the question. In the meantime, Fabio can
Okay.
the microphone. Have you considered, the question is from Martín Castro Manzano. Have you considered something similar, but with Tableau or tree-proof method, which are very diagrammatic?
Yes, they are very diagrammatic. I am not very familiar with, well, I am familiar with Tableau, but not in the model, for the modal logics. So I don't have explored that that subject. Maybe we can also study these diagrammatic proofs that given by the trees and try to make the correspondence. We use the Fitch style systems because they are like more common and more used for teaching, also for other mathematicians that work with. But yes, thanks, Martin. We are going to explore that that area.
Thank you, Lourdes. Fabio, are you ready?
Can you hear me?
Now we can hear you.
Yeah.
Yeah, maybe I'm going to turn off the camera because the internet connection here is really bad. I only want to say that the idea, the first motivation to start this work is that the original work of Clauston, he only says, okay, these rules are equivalent to Fitch style. That's all. And then he starts doing some category theory stuff. And then we wanted to ask to see that why they are really equivalent to Fitch style. And in general, we are interested in deductive systems for modal logic which are not labeled. So it's hard if you don't want labels in the systems. That's why S4 is easy. But if you go to S5, then you need either hypersequence, tree sequence, or a sequence with a stack of context and so on. So this is the starting point, which is the easy part. That's it. Thank you.
Okay. Thank you very much, Fabio. So we are now on time for the next talk, which is by Jose Martin Castro Manzano. And the talk is titled Interpolation in Term Functor Logic. So Martin, you want to stream the video, or you want to give your talk now?
I think the video would be better.
Okay.
Yes.
So we stream the video. Thank you.
Good day to you. My name is Martin, and today I'm going to talk about interpolation for term functor logic. So in this contribution, we attempt to capture some sense of interpolation for Sommers and Engelbrechtsen's term functor logic. Our plan for today is as follows. First, we are going to show our motivation and our goals. Then we will expound some preliminaries. Later, we will explain what we mean by term interpolation. And finally, we will close with some final remarks. Broadly construed, Craig's interpolation theorem states that for any pair of formulas phi and psi, such that phi implies psi, and interpolate is a formula gamma such that phi implies gamma, gamma implies psi, and the non-logical symbols in gamma occur both in phi and in psi. In other words, if we let this expression stand for the set of relation symbols in phi, then Craig's theorem would say that if phi and psi are sentences such that phi implies psi, then there exists a sentence gamma, which is called an interpolant, such that phi implies gamma, gamma implies psi, and the relation symbols in gamma are a subset of the intersection of the relation symbols in phi and in psi. Now, Lyndon gave a generalization of this interpolation theorem, but in terms of the polarities of the relation symbols involved in a given formula. His theorem states that if phi and psi are first order formulas and phi implies psi, then there exists a formula gamma, which is called an interpolant, such that phi implies gamma, gamma implies psi, and every relation symbol which happens positively in gamma happens positively both in phi and in psi. In other words, if we let this expression stand for the set of relation symbols with at least one positive occurrence in phi, then if phi implies psi, then there is an interpolant gamma with respect to the set of relation symbols with a positive occurrence of a term or with a negative occurrence of a term. Now, Wilfrid Hodges has argued rather convincingly that Lyndon's theorem gives a generalization of the laws of distribution for syllogistic, which is a claim we find quite interesting because distribution, which is a particular concept we use when we talk about terms that appear under the scope of a universal quantifier, serves a fundamental purpose in Sommer's and Engelbrecht's term functor logic, which is a novel logic that recovers some insights of the traditional Aristotelian logic, insofar as it helps account for a notion of validity. So, given these preliminaries, we cannot help but wonder, granted these superficial links between Lyndon's theorem, distribution, and Sommer's and Engelbrecht's logic, is there some sort of interpolation for said logic? So, in this contribution, we explore this issue and we suggest that there is indeed a plausible sense in which we could account for some sort of term functor interpolation for this logic. And in order to reach this goal, we first expound the basics of term functor logic together with a sense of term distribution, and we also offer a proof of our main contribution together with some examples, and at the end we close with a brief discussion. Okay, so let us start with term functor logic. So, assertoric syllogistic, which is the logic at the core of traditional Aristotelian logic, is a term logic that makes use of categorical statements in order to capture a basic notion of assertion. A categorical statement is a statement composed by two terms, a quantity and a quality. Typically, we say a categorical statement is a statement of the form quantity S, quality P, where quantity may be either universal or particular, and the quality may be either affirmative or negative, and S and P are term schemes. From the standpoint of Sommer's and Engelbrecht's term functor logic, we say a categorical statement is a statement of this general form, where plus and minus are functors, and of course S and P are term schemes. So, given this language, this logic offers a basic sense or a basic notion of validity as follows. So, in this logic we say a syllogism is valid if and only if the algebraic sum of the premises is equal to the conclusion and the number of particular premises is equal to the number of particular conclusions, or vice versa. So, for example, if we have an argument like this, we can clearly see that minus p plus p cancel each other out, and so we get that the sum of the premises, which in this case would be minus L plus S, is equal to the conclusion, which is condition 1, and also the number of particular conclusions, which in this case is 0, is equal to the number of particular premises, which in this case is also 0. Now, this notion of validity is an algebraic rendition of the dictum de omni et nullo, which is the principle that states that everything that is affirmed of a whole can be affirmed of a part. And so, alternatively, using the concept of distribution, we can define the same notion of validity, but in the following terms. So, let phi of plus m stand for a statement with a positive occurrence of the term m, that is, in other words, that m is undistributed within that statement, and let psi of minus m stand for a statement in which m occurs negatively, or in other words, m is distributed. So, according to this alternative presentation, the dictum de omni et nullo would say that if we have phi of minus m and psi of plus m, then it follows that phi of psi, since minus m and plus m would cancel each other out. Now, this second account of validity for term functor logic depends upon a sense of term distribution as follows. So, given a term t in a categorical statement phi, we say that the term t is distributed in phi if and only if phi is a statement of the form every t is whatever, right? And a term t is undistributed in a statement phi if and only if such term is distributed in the contradictory of phi. Thus, informally, given its quantity and its quality, a categorical statement distributes its terms if and only if they have a universal quantity or a negative quality. That is, if and only if said terms happen next to the minus functor. So, for the purposes of this contribution, let this function over here stand for the set of distributed terms in a categorical statement phi. Then, for example, if the categorical statement is minus L plus S, this function over here would return the set with L, and this function over here would return this set over here. Now, in particular, we posit that in case phi is of this form or of this form, then these functions return an empty set, which makes sense because of the notion of the dictum de omni et nullo. Now, up to this point, given this exposition, one could think that the notion of validity for this logic, for this term logic, only covers monadic or syllogism-like inferences. But that would be a hasty conclusion, because we can extend the previous notion of validity in order to cover or capture relational, singular, and compound inferences by noticing that any categorical statement is a well-formed formula of TFL, and either by enlarging the rules of inference or by implementing tableau proof methods. But in any case, we can accomplish that without losing the notion of term distribution. So we can extend the notion of validity for this logic as follows. So we can say this. Let phi and psi stand for arbitrary TFL well-formed formulas, and inference is valid in this system, which we denote by this expression over here, if and only if psi is obtained from phi by applying some adequate rule of inference or by following a tableau procedure. So, for example, if we have an inference like this, we can apply some rules of inference, for example, and we can see how the dictum "de omni et nullo" is applied. So, given these preliminaries, we can suggest a notion of interpolation for this particular logic as follows. So we say something like this: let phi, psi, and gamma stand for arbitrary TFL well-formed formula. If phi implies psi, then there is an interpolant gamma such that phi implies gamma, gamma implies psi, and every term that happens either distributed or undistributed in gamma happens distributed or undistributed in both phi and psi. Now, since the proof is lengthy, we are going to focus on some examples. So consider this example over here, which is a propositional example. So say we have this inference over here, which is quite similar to propositional logic, so classical propositional logic. Notice that in this case we can find an interpolant gamma that follows from phi, indeed, because minus p plus p would cancel each other out. So from phi we can get this gamma over here, and then from gamma we can use another rule of inference or another tableau procedure in order to show that from plus q it follows that minus minus r minus minus q. So in this case gamma would be plus q, and that would be the interpolant. We can do something similar, but not just for the propositional case, but in a syllogistic case. So over here we have a typical Barbara syllogism, and we can see that in this case the very conclusion works as the interpolant. But also we can develop, for instance, a polysyllogistic case, and in this case the interpolant gamma would be the conjunction of a couple of categorical statements within phi, that follow from phi. Also we can use relations again, so we are not constrained by syllogistic inference, so we can develop relational inferences like this one over here, and again we can show that there is an interpolant. And finally another relational case in which we can see how the interpolant is obtained. So to wrap this up, in this contribution, given some superficial links between Lindon's theorem, distribution, and Sommers and Engelbrecht's logic, we have explored some sort of interpolation for term functor logic, and we think this is an interesting result, at least for a couple of reasons. First, because research on interpolation for this logic has not been attempted yet, as far as we are aware. And second, this kind of research moves the studies on this logic towards new directions that deserve more attention. Now, finally, having reached our goal, we would like to close this contribution by answering some potential objections to the proposal developed thus far. So, this could be one objection. The notion of interpolation is usually defined in relation to results on proof theory, but this proposal doesn't develop any proof theory. Now, the problem with this objection is that it would be false to claim that our result is void of developments on proof theory, since the main theorem requires the notion of proof in term factor logic. It is true, however, that we rely on such results without discussion. Now, a second objection would say that the notion of interpolation is usually defined in relation to results on model theory, but that this proposal doesn't develop any model theory. And similarly, it would also be false to claim that our result is unrelated to model theory, because the main theorem requires the notion of distribution. And this is interesting because distribution is the concept that provides the semantics for this particular logic. And finally, someone may say, well, the notion of interpolation has some clear meaning in classical logic, but there is no clear meaning for this so-called term interpolation. And finally, well, it would be unsound to argue that there is no clear meaning for term interpolation, because term interpolation explains why distribution has been so important in traditional logic. And thank you for your time.
Okay. Thank you very much for the talk, Martin. We have some time for comment and question. Fabio?
Sí, ¿me escuchan?
Yes.
Okay. Regarding your two objections at the end, and you mentioned the article of Wilfred Hodges about distribution, and in that article he uses sequence to formalize syllogism. So the question is that if there are some systems other than Tableau for term functor logic.
Yes, there is. Can you hear me?
Yes.
Yes, there is a natural deduction system developed by George Engelbrechtsen. But well, short answer, yes, there is a natural deduction system.
I have another question, but I don't know if I can proceed.
If nobody else want to ask, I suggest you go ahead, Fabio.
As far as I knew before your last slide, the term functor logic does not have a complete, quite formal semantics. Yeah. But at the end, you mentioned that there is a definition of formal semantics so I want to question if now we have one formal semantics or more advances towards the formal semantics, or what's the status?
Oh, thank you. That is a very interesting question. There is a lot of development on philosophical semantics for term functor logic, but it is true that in terms of formal semantics, there is very little. However, there is some paper in which some author proposes that the very notion of distribution can fulfill the role can fulfill a semantic role in order to give some notion of semantics for term functor logic, so that instead of talking about truth values or yes, instead of talking about root values, we talk about distribution values. And actually, this is not quite new. There was some logician named Colvin Williamson, I believe, that already suggested that we can develop some sort of binary semantics for distribution, because distribution works in pairs, because we have distributed and undistributed terms, so that we can make the notion of distribution like very good. Yes, we can say translate the notion of distribution to a binary logic, so to speak. I don't know if this comments answer your question, Fabio. Yes, but thank you very much.
Yeah, thank you. Thanks.
Okay. So I think we are now on time for the next talk, which is an invited talk. I see Veronica is here. So I want to introduce Veronica. First of all, I want to thank you, Veronica, for accepting giving this talk. And I want to give you a very brief introduction to Veronica. So Veronica is a professor in Universidad Tecnológica de la Mixteca. And let me see. Sorry. I missed your introduction. So well, I will give another introduction. So Veronica is a very good friend of many of us and a very good friend of the workshop from the very beginning. So for us, it's a pleasure to have here Veronica. And well, I will let Veronica to start the talk, which is titled Twisted Structure for Genuine Paraconsistent Logics. Thank you very much, Veronica.
Thank you. And well, I want to thank the committee for the invitation. I'm very glad to be here. And well, let me share my screen. Please tell me if you can see it now.
Yes, it's okay.
Yes.
Okay, thank you. Well, as Everardo said, I'm going to talk about twist structures for genuine paraconsistent logics. And well, this is a joint work with Alejandro Hernandez-Tello, and we work in the Institute of Physics and Mathematics here in the Mixteca in Oaxaca. And well, we're far away from Mexico, from Puebla, and from France, but I hope that you enjoy this talk. Okay, well, we will start with a short introduction, some basic concepts. First, I have to define what is a genuine paraconsistent logic. We are going to focus on the three-valued case. I'm going to present you a big family of this kind of logics. I'm going to give you a particular example of, well, the whole picture of what this kind of logic contains. And finally, for this family, I'm going to talk about what were our beginnings, their axiomatization. Later, I'm going to talk about twist structures, which is the idea. First, how twist works, and after, well, the definition, the formal definition of twist structures, particularly what kind of snapshots, whatever it means, I'm going to tell about, are for the family GP3, and finally, an example of a twist structure and an axiomatization for one of these logics in the family. Final conclusions and some references. So, well, let's start. First of all, as we know, there are some laws of thought that have been for centuries among us. The law of identity, which informally says that a thing is what it is. The law of no contradiction, that it's impossible for any being to possess a quality and at the same time not to possess it. And the law of exclusion, which says that it's impossible to be and not to be the same thing. Well, these three laws were used and accepted for a long time. However, some important logicians were interested in the violation of these laws. Some of them were, for example, Brouwer, that at the beginning of the last century created a logic in which the excluded middle didn't work. Another one was Vasiliev, that approximately in the same decade, he proposed a logic in which non-contradiction was not a theory. And finally, Lukasiewicz proposed a logic in which none of the second and third law were valid. That's non-contradiction was not valid and excluded middle also was not. Well, so the idea of not having these laws in our logical system is not new. Have a lot of time, there are a lot of systems with these particularities. Classical negation for a given logic is semantically characterized by properties. The first one associated with a non-contradiction that said that for non-sentence, phi, it's the case that phi and not phi are simultaneously true. And on the other side, the law of excluded middle says that for no sentence phi, it's the case that phi and not phi are simultaneously false. So in terms of multiple conclusion consequence relation, both laws can be represented as we have here, the schema in C and the schema in M. In the left side, the commas will represent conjunction, what are changed by disjunction in the right side. So we can define then the notions of paraconsistency and paracompleteness. In this case, logic will be paraconsistent if the principle NC does not hold. That's it's not possible to have phi and not phi. In the case of paracompleteness, we have that a logic is paracomplete if the principle IM does not hold, and that it's that we cannot have the security that we have phi or that we have not phi. Well, the problem begins that with the traduction with the principle NC, which it's not always expressed as the way we look here. Sometimes can be also seen at this with as this principle NC prime, which is the negation of the conjunction of phi and not phi. Similarly, we can have the idea of doing this, but not with the principle NC, but with the principle AM. And well, the thing is that this goes or allows us to define a genuine paraconsistent logic. So a genuine paraconsistent logic is a logic that rejects both NC and NC prime. And well, in formal terms, we are saying that these two properties are held by logics that are paraconsistent in a genuine way. As I said, something similar occurs with AM, in which we can an alternative representation, which is this. We have that it's not the case that phi or that phi or not phi, it's true. And well, that allows us to define the dual notion of genuine paraconsistent logic, that is a genuine paracomplete logic. And in this case is a logic which satisfies GP1V, which is a dual of GP1, and GP2 dual, which is a dual of GP2. As we can see, these notions are closely related, and the dualization is really natural by the classical De Morgan laws. So the long story, what have we or what have we been doing in the last years? Well, analyzing the negation, and as we can see, there are two principles related to this connective, which is the law of contradiction and the law of excluded middle. As we see in the previous slides, we can represent these two principles in different forms. And the thing is that these forms are not equivalent, so they ask for different conditions over connectives. If we focus on the non-contradiction side, the principles NC and NC primes allows us to define a genuine paraconsistency, and in the other sides, AM and IM allows us to define genuine paracompleteness. So BSU defined two genuine paraconsistent logics, which are L3A and L3B. And later we rescue L3C and L3D. After that, we start our process of axiomatization of these logics, but we also were interested in the genuine paracomplete counterpart. So we find that these four logics have their duals in the paracomplete counterpart. And when studying, we were interested in expand the language, not only considering negation and conjunction in the case of paraconsistency, or disjunction in the case of paracompleteness. And we got a new big family, which we call GP3 dual. And well, we started with this part, and we characterize the whole family. We found twist structures for this, and we find axiomatizations for the whole family. So we wanted to go back and do something similar with the paraconsistent family. So that's what I'm talking to you today. We are going to talk about this family named GP3. So let's start with some basic concepts. I hope not to be too fast in this part, but I think that are, background that it's well known for the community. Well, if we have a language, we say that a logic L in this language is a pair, which is the language and a relation, which is a structural non-trivial Tarskian consequence relation. And in the case that implication is one of the connectives in the language, we will ask that it will be closed under modus ponens. Particularly, considering this consequence relation, we can define what is a conjunction, disjunction, and implication with these usual characteristics. For example, we will say that a connective is a conjunction if whenever we can derive phi and psi, it's because we can in independent way derive phi and psi, and the converse also holds. The case for disjunction is if we can derive some formula having as hypothesis that the disjunction of phi and psi holds, then if we have by its own side phi and psi, we will derive sigma using only one of the two hypotheses, and also the converse. And finally, we will say that connective is an implication. Well, if we can prove or derive psi having phi as hypothesis, and that this allows us to take the hypothesis and send it as the antecedent of the implication and the formula that we had as the derivation as a consequence. Well, I'm going to skip this, which we are not going to use a lot in the following, but classical implication is just an implication that satisfies these three characteristics. So we are going to introduce our logics using the matrix semantics. So a matrix will be a structure which has a non-empty set, which is called the set of truth values, or it's the domain. A subset of it, which is not empty, will be the set of designated values. And finally, for each connective in the set of connectives in our language, we will have a function associated to it, which will be the truth function for the connective in question. In this case, notions as valuation, validity, tautology, and consequence are defined as usual. And well, if we have a matrix, we can induce a consequent relation. And that's if we have a set of formulas gamma and a formula phi, we will say that they are related under the consequence relation induced by the matrix if every model of the set gamma is a model of psi. So the logic L sub M will be the logic created with the language in question and the consequence relation induced by the matrix. An interesting and important notion is the neoclassicality. The neoclassicality is just a way of see the set of designated values as a unique value, which can be identified with 1 in the case of classical connectives, and this D with an overline will denote the set of not designated values. So we will say that a conjunction is neoclassical if the valuation of a conjunction is designated if and only if the valuation of each of the conjuncts are designated. Something similar for disjunction. A disjunction will be neoclassical if whenever the evaluation of the disjunction is not designated, is because because the disjuncts are not designated and vice versa. And finally, an implication is neoclassical if the implication is designated on if and only if the antecedent is not designated or the consequent is designated. So this will be very useful in our definitions. Finally, a multi-valued operator will be a conservative extension of a b-valued operator if the restriction of the connective to the values of the b-valued operator consist. And a multi-valued operator will be called molecular if the range of it is a proper subset of the set of values. Okay, So, as I said, we are interested in the case of three-valued genuine paraconsistent logics. These will be logics in the language of negation and conjunction. There are only 4 of these kind of logics. They can be induced by a matrix which has 0, half, and 1 as truth values, and 1.5 as designated values. And well, how are their truth tables? Well, the first one, called L3A, is defined using this table for negation and this one for conjunction. As we can see, since 1.5 are the designated values, in the case of negation, we have a value whose negation is designated and the original value is also designated, which allows us to have a paraconsistency. On the other hand, the conjunction, we asked to be a classical, an extension of classical logic, which fix the values in the 4 corners. I mean, 0 and 0 will be 0, 0 and 1 will be 0, 0, well, 1 and 0 will be 0, and 1 and 1 will be 1, as in the classical case. And since it's neoclassical, we will fix this as not designated, and this is 0, and this one as not designated, and this will be 0, and only the values in these 3 positions will can change for get the different logics in this family. This is the logic L3A. As we can see, if we change the negation and if we change these values here, we have a second logic in this family. The third one is using the same negation that L3A, but with a different conjunction. And finally, L3D has similar behavior. In this case, the negation changed, but the conjunction is the same for L3C. Well, in a previous edition of the Lanmr, I presented the whole study, the deep analysis for get these 4 logics and how are the unique logics in the family of 3-valued logics that satisfy these conditions. Well, now the thing is that we are interested in expand our language and add some other connectives. So the first is to add a disjunction. So if we want to add a disjunction and we want that it be a conservative extension, then we have to fix the 4 values that are squared, that are in the corners. If we ask for neoclassicality and symmetry, then we have 3 different variables to be determined. D1, D2, and D3. Since we have that we want neoclassicality, the only non-designated value will be the case of 0 disjuncted with 0, which means that the rest of entries in this table must be designated. This gives us 8 different disjunctions just by changing D1, D2, and D3 among the possible designated values, which are a half and 1. So these are the different disjunctions that we can add to or 4 previous logics to expand its language. If we are interested in expand the language with an implication, then something similar happens. Since we want that the implication is a conservative extension, then we have to fix these 4 values that are squared. And since we are asked for neoclassicality, then we have to set this entry as 0, and the rest of entries must be designated, which means that they must have a value of half or 1. Since there are 4 different variables and each one of them can have one of 2 different values, we will have 16 different implications. Here we have the first 8 that had been named within implication with a subindex. Here we have the case from 0 to 8, in which we can see that only these 4 entries are changing from one to another. And in this new page, we have the other 8 implications. Well, so what we obtain is a big family of logics. If we set X in one of the 4 different letters A, B, C, and D, if we select an index I between 0 and 7 and an index J between 0 and 15, then we can expand the logic L3X with X, A, B, C, or D with a disjunction E with E in this set, and finally an implication J with J in this set of values. And this logic will be called L3X I and J. So we have a big family of genuine paracomplete logics, which are three-bowed and will be denoted by GP3. And by the conditions that we have, we are setting 512 different logics in this family. So the picture is a little big, but it's not as difficult as it could seem at the beginning. For example, just to take one of these 512 logics, we will take the logic L3A, which has been expanded with disjunction 3 and with implication 6. And well, this means that the matrix will be with these 3 values. The designated values will be these ones, and the truth tables for the connectives are the following. I mean, the negation will be the negation 0, the conjunction will be the conjunction 0, and this forms the logic L3A. And then we expand with disjunction 3 and with implication 6. If we see, we can do this, as I said, for each of the 4 basic logics, and adding one of the disjunction and one of the implications. Well, okay, now what do we have is a big family, but now what can we do with this family? Well, we started to get axiomatization for this family, for these logics. Particularly, we start with L3AG, which is exactly the logic I presented in a previous slide. L3A with disjunction 3 and implication 6. We originally named L3AG because, as you can observe, if I go back, this implication is the Gebel implication. So that's the reason to give this original name. But since now they are into a big family, well, we have renamed using the corresponding indexes. So the problem is how to get an axiomatization for these logics in the family, and the thing is to do it in a systematic way, because using Lanmr's technique means that for each system we have to identify the truth values as a specific scheme on the logic, and well, literally give a set of axioms into the well, translate the truth tables into schemes, one for each entry in our tables for each of the connectives, which is a very big task. And if we want to do it for each of the different logics in the family, it's a huge work. So we need to find a different way to achieve this goal. And the solution was to construct a bridge using twist structures to cross from matrix semantics to axiomatization. And how did we do that? Well, here's the story. First, what are twist structures? Well, twist structures were developed by Fidel and Bakarelov around 1978, and they were an alternative presentation for the algebraic semantics of Nelson logic N, which has a strong negation. The twist structures are just a class of algebras whose domain is a subset of cross product of two sets. One is a Hating algebra, and the other one is the dual of the Hating algebra. So the dual in the second algebra is the twist, since the dual is just reversing the order, and that's why its name is twist. And the second component is just an interpretation of what is the behavior of the strong negation in the logic. In general, twist structures have been used to set semantics for non-classical logics, and particularly to paraconsistent logics. So that was a good idea to use them for our family. We followed the ideas of Carnelli and Coniglio, and we give some conditions to analyze the twist structures for this family. As we can see, we will have pairs A and B. These pairs will be called snapshots, as a picture of what's going on with the formulas. Particularly, the first entry will say what's going on with our formula phi, and the second entry, what's going on with the negation of the formula. All the logics in the family GP3 are expansion of classical logic if we consider the positive fragment and the negation, this classical negation defined as a formula implies the bottom constant, which is a classical negation. The snapshots also are taken over a Boolean algebra, and since the exclude middle is valid, we must ask that the first component in disjunction with the second component must be 1, must be true. And finally, since we have two designated values, they will be the snapshots which the first coordinate is 1. In fact, what we are doing is just identifying the values 0, half, and 1 with these pairs. And what we are going to do is to define the operators negation, conjunction, implication between these snapshots. The idea is that the first component will say us which is the value of the formula, and the second component which will say what's the behavior of the negation of the formula. So, for example, if we have the negation of a pair, will be another pair in which the first component must be the negation of the first component, and the second component will be the negation of the second component here. Since the snapshots are related with the formula and the negation of the formula, then we are comparing what's going on with the negation of a formula. And since not in all the logic we are considering the negation is involutive, then we will have different values for C and D. So we are taking the Boolean algebra with domains 0 and 1. So in this case, the available snapshots are only 3. Top, true, and bot, where top will be the pair 0, 1, which means that the formula is 0 and its negation is, that the formula is true and its negation is false. T, which will be the interpretation that a formula is true or it is designated and its negation is also designated. And finally, bot, which means that the formula is false or not designated and its negation is designated. In this case, we have that top and T are designated. So the twist structures for our family will have some special restrictions. I mean, there will be some extra conditions for conjunction, disjunction, implication, negation, and of course for the bottom particle. First, we have that the bottom particle will be identified with the pair 0, 1. Then, if we have the negation of a pair, the negation of a pair will be the snapshot. In a moment, we will see which are the snapshot for each of this logic. The snapshot for negation 0, if we have that the letter of the logic X is A or C, will be the snapshot for the negation 1 if the X here is either B or D. And we will have that the conjunction of a pair will also depend on the snapshots that we are taking. If we have the conjunction 0, the snapshot will be the corresponding for the case X is A, the snapshot for conjunction 1 if X is B, or the snapshot for conjunction 2 if X is either C or D. And finally, we have to add the disjunction and the implication. So the disjunction depends on the disjunction we have added, and the implications depends on the implication we have added. So what are these snapshots? Well, these snapshots are, the pairs which says what is the behavior of each of the connectives over the pairs. For example, the snapshots for negation 0, or the truth table for negation 0 is this one, in which the second component is the negation of the first. Since B is the negation of the first, we have to set the first component as B, and the second component must be the negation of B. But in this case, this negation do not coincide with A, since this is not involutive and is the classical negation of B. The snapshot for negation 1 is this one, in which we can see that negation is involutive. These are the snapshots for the 3 different conjunctions that let us define the family with the 4 different logics, L3A, L3B, L3C, and L3D. And particularly these ones which are in red are the ones for the logic L3A, which we take as example. Later, if we want to add one of the 8 different disjunctions, we will have to check the snapshot for each of the disjunctions. Particularly, the one in red color is the snapshot for the disjunction 3, which is the one that we selected to expand L3A. And well, in the next slide, we have the list of snapshots for the different implications, and particularly in color red, we have the snapshot for the 6th implication, which is the one that we selected for our logic. So if we take these snapshots taken that were in red, we will have the twist structure for the logic L3A with disjunction 3 and with implication 6. So it will be a twist structure over a Boolean algebra in which the disjunction of the first and the second component must be 1, and where the connectives over pairs are defined as follows. First, the interpretation of the bottom particle is the pair 0, 1. As we see, the second component of the negation is not B, but with this classical negation. The interpretation of the conjunction in the second component is this formula in terms of the 4 components, A, B from the first pair, and C and D from the second pair. And well, after that, we add the disjunction and the implication characterization of the connectives. So at this point, what we have is a different semantic for our original logic, which was defined using matrix semantics. With this twist structure, we can, in a very, very easy way, get an Hilbert axiomatization of our logic. First, we will start with the positive part of propositional logic, classical logic, and we will add the following axioms. First, the exclude middle after a scheme that says the behavior of the bottom particle, and well, one action for each of the connectives. In this case, the action for negation, the action for conjunction, the action for disjunction, and finally, the action for implication. As we can see, again, I put them, well, part of them in red, because these parts are the ones that are translated from the twist structures. For example, see here, we have the classical negation of the paraconsistent negation of alpha. That's the double negation of alpha. Let's go back and see what's the snapshot for negation. So if we go back to the back slide, we have that the negation of the second coordinate in a pair will be the classical negation of the B, which is the second component of the pair. But if we remember, the second component of the pair represented the negation of the first component. So this B is the paraconsistent negation of the first component. That's why we have the classical negation of the paraconsistent negation of A in our actions. So if we can see, we have the classical negation of the paraconsistent negation of alpha. In a similar way, we have the characterization of the negation of a conjunction. In the second component, we are seeing which is the behavior of the negation of a conjunction, and is this one. As we can see, is the negation of A, which is the first component, disjuncted with the negation of C, which is the negation of the first component of the second pair, disjuncted with B conjuncted with D, where B and D are the second component of the pairs. So this, in terms of formulas, will be the negation of the first formula, the negation of the second formula, in this case, classical negation. And then we have here, if you remember, B and D. But B is the negation of alpha, and D is the negation of beta. So this is the literal translation of this second entry in the pairs of twist structures. Similarly, the disjunction and the implication are obtained. So at this point, what I have shown is a particular example for the logic L3A with implication 3, with disjunction 3 and implication 6. But the same idea can be used for any of the 512 different three-valued genuine paraconsistent logics, changing these 4 axioms according to the snapshots of each of the connectives used in its definition. The negation and the conjunction depends on if we select L3A or L3B or L3C or L3D, and the 2 final axioms that refers to the behavior of disjunction and implication will depend on the snapshots for the corresponding disjunction and the corresponding implication. So, well, here ends the story. And what we have is that first, the notion of genuine paraconsistency was presented around 2015. Later, we studied how the logics, particularly L3A and L3B, could be expanded with suitable implications. Later, we get axiomatization for 2 of these expansions, but in terms of Lanmr's technique, which was a good idea, but not useful when you want to axiomatize a family of the size we are getting here. And well, we did a deeper analysis over this family. We found 512 different logics. All of them extend conservatively the classical truth tables, and whose positive connectives are neoclassical. So we construct the twist structures for each of these logics, and that allows us to get axiomatization for each of the logics in the family. And well, that's it. Here we have some of the references in which you can find well, the main concepts and ideas in the talk. First, the seminal paper of Jean-Yves Bessieux, where genuine paraconsistent logics are defined. Originally, they had the name of strong paraconsistent logics. However, the term strong was already used for other kind of paraconsistent logics, so it was changed to genuine. Here we have, well, in fact, a volume which has a lot of information about paraconsistent logics, particularly the way twist structures can be used to give semantics to paraconsistent logics. Here you can find the axiomatization of these 2 logics in the family we are describing, but as I said to you, it was using Lanmr's technique. And well, here you can find the expansions of logic L3A and L3B with the Gödel implication. And well, that's all for my part, and I hope you have enjoyed the presentation. And well, I let you the remaining time for questions.
Thank you very much for this presentation, Veronica. I think the presentation was very clear, as usual, with you, of course. Well, we have time for some questions. Pregunta Miguel si las preguntas pueden ser en español.
I don't know, I suppose.
Sí, claro.
Hola a todos. En español, para que sea un poco más precisa mi pregunta, en inglés a mi ardilla, a mi cerebro le cuesta un poco más formularla. Entonces, si no hay algún inconveniente, mi pregunta es la siguiente. Berito, muy bonito trabajo. Se ve que han trabajado bastante con las estructuras genuinas de las lógicas. Me queda una duda. Platicando alguna ocasión con uno de los autores que tenías por ahí, que han trabajado con las estructuras twist, yo me quedé con la idea de que una estructura twist es cuando tú deseas encontrar la semántica algebraica o el álgebra de la lógica de un sistema axiomático. O sea, a lo que voy es, tú debes de tener, y tengo entendido, y si no es así, corrígeme, debes de tener primeramente el sistema axiomático, y una vez que lo tienes, encontrar la estructura algebraica. El problema aquí con la estructura twist, al menos en el libro que nos regalan Coniglio y Carnielli, es que creo que hay uno de sus resultados mencionan que cumpliendo una serie de características en la lógica, tú puedes asegurar cuál es la estructura twist, pero nunca se te dice cuál es. ¿Cuál es el problema de esta situación? Que la estructura algebraica no sabemos si es booleana, de Hating, o algún tipo de anillo, grupo, etcétera. Entonces, me queda un poco de duda en lo que fui entendiendo de tu presentación. Primero encontraron la estructura twist, posteriormente encontraron la axiomatización. Me queda un poco de duda porque, por lo que yo entiendo es, debes de tener tu sistema axiomático y generalmente esos sistemas axiomáticos vienen presentados por teorías maximales. Ocupan por ahí, creo, el lema de Lindenbaum-Loss y posteriormente trabajan con la estructura twist. Entonces, me queda un poco de duda. ¿Era correcta esa idea que en algún momento discutí con uno de los autores de esta técnica?
Ok, bueno, creo que sería un poco más fácil responder en español. No sé si Sofi nos esté escuchando, espero que esté, o que no esté, ya no sé, para que no la deje fuera de la discusión.
Se excusó un momento de la reunión.
Ok, entonces, bueno, a ver, primero, no puedes decir que fue primero si el huevo o la gallina, ¿no? O sea, tú puedes tener un sistema lógico definido en términos semánticos y tú puedes tener un sistema lógico definido en términos de teoría de prueba, cualquiera que sea la teoría de prueba, cualquiera que sea la semántica. Okay. Lo interesante, pues, es justamente hacer un link entre esas dos cosas, es decir, probar robustez y completez. Cuando tú logras hacer eso, pues lo único que estás diciendo es, pues fíjate, este sistema de demostración que tengo aquí corresponde con esta semántica que tengo acá Y entonces, pues tú puedes transitar libremente. ¿Quieres ver que algo es demostrable? Pues vete a la semántica y verifica que es una tautología. O si tú tienes algo y sabes que es una tautología, pues entonces significa que debe de ser demostrable del otro lado. ¿Sale? Entonces, en ese sentido, pues tú puedes, insisto, tener primero la semántica y tratar de buscarle una teoría de prueba, o al revés, tener una teoría de prueba y andarle buscando una semántica. En ese sentido, entonces, pues no importa de qué lado estés. Nosotros habitualmente, o en muchos casos, pensando en estas lógicas multivaluadas, hemos ido pues siempre de la semántica a la teoría de prueba, es decir, tenemos la semántica, tenemos el conjunto de tablas de verdad y queremos ver qué axiomas nos sirven para pues tener una lógica o un sistema de prueba para esa lógica que sea robusto y completo. Entonces, bueno, pues eso ya dice que no es forzoso que tengamos primero una teoría axiomática para luego irse a las twist structures. Luego, lo que mencionabas respecto a que si sirven para pues darle una semántica algebraica, pues las twist structures son álgebras, ¿no? Es un tipo particular de álgebras con un dominio muy, muy particular, un dominio que es un producto cruz entre un álgebra y el dual de esa álgebra. Entonces, como el dual de la álgebra habitualmente lo que haría es revertir el orden, entonces por eso es que son las twist structures, ¿no? Tengo yo un orden de un lado, un orden del otro lado, a este le doy vuelta y pues ya la corregí, ¿no? Ahora, dependerá completamente de la lógica que tú quieras caracterizar con estas estructuras, si lo que puedes meter en la primera y segunda entrada de ese dominio son álgebras booleanas, son álgebras de Heyting, son solamente retículos con algunas características. Eso dependerá completa y exclusivamente de la lógica que estés tratando de axiomatizar. En este caso, dado que solo tenemos 3 valores, basta con tomar una álgebra booleana. De hecho, ni siquiera estamos tomando las 4 parejas de la álgebra booleana. Nada más estamos tomando 3 de las 4 parejas. La 1, 0, la 0, 1, que serían los valores clásicos, y el 1, 1, que sería el valor para consistente, o sea, el que la fórmula es designada y su negación también es designada. Entonces, pues claramente, como decías, para realizar una demostración de robustez y completez con los sistemas propuestos, se tiene que acudir a hablar de conjuntos saturados y se tiene que utilizar el teorema o, bueno, la técnica de demostración de Lindenbaum-Loss. Entonces, sí, para cada uno de estos 512 sistemas se tiene que hacer una prueba de ese tipo, pero dada la forma en la que se construyeron los axiomas y la caracterización que se tiene de los conectivos con estas twist structures, es decir, los snapshots en las segundas componentes, la prueba sale directito. Entonces, pues esa es la ventaja justamente de tener las twist structures. Entonces, nosotros ya teníamos una semántica, que era la de matrices, y queríamos una axiomática. Pero ir directamente entre matrices y axiomática, utilizando Calmar, no iba a funcionar por la cantidad de análisis que teníamos que hacer. Y entonces, pues lo que hicimos fue, pues lo que dije, ¿no? Crear un puente. Entonces, si no puedo ir fácilmente de aquí para acá, pues entonces voy a pasar de la semántica de matrices a la semántica de tipo twist y de tipo twist a la axiomática, paso fácilmente. Entonces, pues ya construí mi puente y ya de cualquier semántica de matrices puedo pasar a la axiomática y obviamente el proceso inverso. No sé si eso pues aclare la duda.
Sí,
Espero
sí,
no haberme extendido demasiado.
entendí el puente que manejan, pero ¿no hubiera sido más sencillo, quizás, no lo sé, realmente yo no he estudiado muy a fondo la estructura twist y de Fidel, las conozco muy vagamente, pero ¿no hubiera sido más sencillo que en lugar de trabajar la técnica de Calmar, que puede ser muy difícil o complicada por su elaboración, es muy rústica, es muy tradicional, trabajar directamente con la teoría maximal, trabajar con Lindemann Laws para hacer la axiomática, creo que con esa metodología es más sencillo encontrar la axiomática y luego ocupar el resultado que Carnielli y Coniglio tienen, que dicen, pues sí, mi teoría es maximal, ocurren estas cosas, pues ya sé que puede existir una estructura twist. No lo sé.
Sí, el punto es que ahí vas un poco a ciegas para saber cuál es el conjunto de axiomas que debes de meter. O sea,
Okay.
Calmar es lo que hace, ¿no? Decirte qué axiomas te van a permitir completar, ¿no? Si no tienes Calmar, tendrías que buscar alguna otra herramienta para distinguir cuáles serían los esquemas que debes agregar para, pues ya luego aplicar, teorías maximales y Lindemann-Loss. Si no tienes tú tu propuesta de cuáles son los axiomas, pues no, no jala la prueba. Entonces aquí el punto es cuál sería la estrategia para definir esos axiomas, ¿no?
Vale.
Probablemente digo, no es imposible, haya otras formas, ¿no? De inferir cuáles son los axiomas que debes agregar, pero pues las twist structures nos permitieron eso, ¿no? O sea, ver exactamente cuáles son los axiomas que debes de agregar para garantizar robustez y completez.
Vale, muchas gracias.
Jesús alzó la mano hace rato. Le damos la palabra, por favor.
Hola, Vero.
Hola, ¿qué tal?
Gusto saludarte.
Gracias, igualmente.
¿Cómo estás?
Bien.
¿Tú y Alejandro bien?
Bien, gracias. Aquí, como siempre.
¿La nena bien también?
Enclaustrados. Sí,
¿Siguen
aquí.
enclaustrados?
Sí.
Qué horror.
Enclaustrados en la UTM.
Bueno.
No en casa.
Ok, ya es una ventaja. Oye,
Sí.
muy interesante todo este trabajo que han venido desarrollando. No sé si, bueno, mi pregunta es, ¿han considerado ver cómo integrar todos estos desarrollos que han hecho en lógicas descriptivas, por ejemplo?
La verdad es que no nos hemos metido en esa parte de lógicas descriptivas. No hemos expandido nuestro lenguaje más allá de lo natural por el tipo de lógicas que estamos definiendo es pues expandirlo con, por ejemplo, operadores que recobren consistencia o operadores que recobren completitud, ¿no? Dependiendo si son para consistentes o si son para completas. Quienes conozcan un poco de la literatura, les llamamos, ¿no? El bolita blanca y el bolita negra. Y sí tenemos algunos resultados en esa dirección, pero es de ese tipo. Cuestiones modales, aún no hemos pensado en cómo expandirlas, pero sí tiene mucho sentido. Entonces sería bastante interesante hacerlo.
Serían pues una aportación muy importante, ¿no? Porque justamente pues el origen de las lógicas para consistentes era ese, ¿no? Es poder tener un sistema que pueda manejar la inconsistencia, ¿no? Entonces, y pues las lógicas descriptivas pues se encargan de eso, de razonar sobre información, son la base de las ontologías, por ejemplo, ¿no? Entonces sería muy importante, muy interesante que tuviéramos una ontología para consistente. Muy bien, muchas gracias. Para completa, claro. Pues muchas gracias
O ambas.
por mi parte. Pues quién sabe qué tanto se pueda, ¿no?
De hecho, bueno, ahí andamos. Ahorita ya el siguiente paso es ese. Ahora no solo quiero para consistencia, sino también quiero para completitud y pues es saltarse a los 4 valores.
Eso, muy bien. Muchas gracias, Vero. Saludos.
No, gracias a usted.
¿Alguien quisiera comentar algo más? Ok. Bueno, pues entonces concluimos agradeciendo a Vero una vez más su participación. Aplausos, por supuesto. Y pues ahorita tenemos una pausa hasta las 11:35 y regresamos.
55.
Perdón, sí, 11:55, perdón, estamos a 11:35, 11:55. Nos veríamos 11:55, por favor.
Ok,
Muchas gracias.
bye.
Muy bien.
Hi, everyone. We continue with the talks of our event. Are you ready? Well, the next talk is a for-valuate logic that extends the paraconsistent G prime tree logic by Mauricio Osorio and José Luis Carballido. Are the authors here?
Mauricio,
Sí,
¿te parece?
sí estoy acá, pero yo nomás iba a contestar preguntas. No sé si la puedan pasar porque ni siquiera la tengo. Creo que José Luis se las envió.
Okay.
Good morning. In this paper, we will talk about a high-value logic that, as far as we know, has not been explored before. Okay? The study of logics plays an important role in areas of artificial intelligence, as for example, knowledge representation. Many logics have been studied before, and the relationships that exist among them is of great theoretical interest. There are two kinds of logics used as formalism of semantics in non-monotonic reasoning. Intermediate logics like intuitionism and Gödel logic with three values, and the paraconsistent logics as C omega and Z. All these logics preserve some important properties of classical logic. Actually, one of the main properties of a good logic is that it preserves a great part of classical logic properties. One can define several semantics in the study of non-monotonic reasoning. Two of these semantics that have great relevance are the stable semantics and the p-stable semantics. The stable semantics can be defined in terms of intermediate logics. The p-stable semantics can be defined in terms of paraconsistent logics. So these groups of logics complement each other, and these semantics are used in non-monotonic reasoning. All logics presented in this paper satisfy some rules or axioms, see, or theorems. One very basic logic is the positive logic. It does not have any negation. And as you see, many of the rules are common sense. Like here, from A, we can know that B implies A. Or from A and B, we have A. Or from A, we have A or B, etc. Right? So these are nice properties that we would expect any logic to possess them. Modus ponens is the only inference rule in this logic, as in many of the logics we mentioned in this work. C omega is a very important logic, at least from the theoretical point of view. It's defined by the axioms of positive logic as the following two axioms. See? A or no A, and no A implies A. See? Those are valid rules in classical logic. However, in C omega logic, we don't have the other two rules are true, right? It's not true that A and no A, and the explosion principle is not true in C omega. These other two rules are also valid in classical logic. So the fact that the last rule is not valid in C omega, the explosion rule, is what makes C omega a paraconsistent logic. So basically a paraconsistent logic is a logic that has a negation for which the explosion principle is not valid. Right? Now C omega has some important properties. It has a minimal property in the area of paraconsistent logics. The minimality consists that in any other paraconsistent logic in which the formula, this negation of A and no A, is not valid, must contain all theorems of C omega, right? So many of the paraconsistent logics are going to contain C omega, or all of them. G3 prime logic is a logic that extends C omega. See? And it has, it's a three-valued logic, but also have a Hilbert-style axiomatic version called Gluck G. That's every tautology in G3 prime is a theorem in Gluck G, and vice versa. Every theorem in Gluck G is a tautology in G prime 3. The values for G prime 3 are 0, 1, 2, and 2 is the only designated value. Well, let's go to the next slice. Here we have the domain of the values for the G3 prime. It is 0, 1, 2. 2 is the only designated value. The conjunction and the disjunction are defined as the minimum and maximum of the two values, respectively. And the negation, well, and the implication, we have formulas for them, but we can also have truth tables for the negation. The negation of the value 0 and the value 1 is 2, and the negation of the value 2, the designated value, is 0. And the implication is here. Actually, the Gödel logic has all the same truth table, except that the negation of 1 is 0 in G3. So there is only a small difference between the definitions of G3 prime and the Gödel logic G3. Well, now the axiomatic system for G3 prime, which we call Gluck G, see, contains all those nice axioms for C omega, the positive logic plus those two axioms of C omega, and some other axioms that are written here. They look a little bit complex, but of course the idea is not that we assimilate these formulas, right? But we need the introduction of 5 more axioms, and even one extra negation, or one non-native primitive connective. That's a negation as defined by the original negation by means of this formula. Alpha implies parenthesis negation of alpha and the double negation of alpha. That defines Gluck logic G. So any theorem in terms of the axioms is a tautology in G3 prime, and any tautology in G3 prime is a theorem in Gluck G. Right. Now, what's new? What about our new logic? And we call it M4, M4, right? It has the domain of values 0, 1, 2, and 3, and 3 is the only designated value. It's a conservative extension of G3 prime, right? How we define this logic? Well, the conjunction and the disjunction are defined in the typical manner as the maximum and minimum of the two values, respectively. It counts with two negations. They are defined here. See, one of the negations is defined by the value of the negation for x is 3 minus x. See, here 0 is mapped to 3, 1 is mapped to 2, 2 is mapped to 1, 3 is mapped to 0. This is the definition also of the Lukasiewicz four-valued logic. And the standard or weak negation, which sends all the values 0, 1, 2 to the designated value, and the value 3 is sent to 0. So then these are the two negations. These two negations are independent. Each of them cannot be defined in terms of the other one with the other connectives, of course. The implication is defined by the following table, but this table. See, the one thing to observe here is that, well, 1 implies 0 has the designated value, but 0 implies 1 also has the designated value, right? See here we have 0 implies 1 has the designated value. So that would be a little bit atypical, right? But in part is one of the reasons why this logic is interesting, right? That is going to have some problems when we try to prove a substitution theorem for this logic, of course, right? And we'll see the example. Now, the restriction of this logic to its values 0, 2, and 3 coincides with logic G3 prime if we interpret the values 2 and 3 as the values 1 and 2 of G3 prime, right? So, in particular, a tautology in M4 is also a tautology in G3 prime. But that's not only the case. It turns out the converse is also true. A tautology in G3 prime is a tautology in M4, right? The proof is done by induction and by using the axiomatic version of G3 prime. That's the Gluck logic, as it is shown in the paper. Here we have some tautologies in M4, as we see, right? The Morgan laws are valid for the two negations. See, we have the strong negation implies the weak negation. The converse is not true. And we have the equivalence between mono alpha and alpha for every atom alpha, right? We have this other formula here that's going to help us to exhibit some property. This formula, when we put the value 2 to alpha and beta, it's going to be 0 on one side and 1 on the other side. So that means, because of the implication table, that's telling us that these are equivalent. The symbol equivalent is interpreted as commonly in logics, right? Is A implies B and B implies A, right? So this is going to be a tautology, see? But we are using the fact that 0 implies 1 is also 3. Now, if we took this is the last, is the same as the last formula we had, the last tautology, right? And we were saying if alpha and beta take the value 2, we are going to have 0 on one side, 1 on one side, right? And that's a tautology then. But however, if we put a negation in front of the two sides, we get this formula. Now, in that case, one of the sides is going to evaluate to 2 and the other one is going to evaluate to 3 when alpha and beta take the same value 2. So this is no longer a tautology, right? So that means the substitution theorem does not work in this logic, right? But there is something interesting. We can define a new connective, non-primitive connective, a kind of strong equivalence defined by means of this formula. Alpha is strongly equivalent to beta if is by definition alpha if and only if beta, and no alpha if and only if no beta, with the strong negation. Now, with this formula, we solve the problem, and we get a substitution theorem, right, for logic M4, right? So that's a nice result for this logic. It's a result that would be is always desired for any logic, right? So then we have so far that M4 is a conservative extension of G3 prime, satisfied actually all the De Morgan laws, see, with the two negation, see, satisfies a weak form of the substitution theorem, and there is much to explore in this logic and its relation to some other better known logics, right? Among those properties we We can study, for example, the normal forms of this logic, well, some other things, right? So basically that's what we wanted to say about this logic. There is too much to be done with this logic, and our names are here, our emails are here. So we thank you so much for listening to this small speech. Thank you.
Okay. Jose Luis is not here, but thank you very much, Jose Luis. Your talk was interesting. We have time for comments or questions. Any questions here about the topic? Okay. Master Osorio, do you want to say any more about this topic?
I have a question.
Okay. Jose Lavalle, Professor Lavalle, go ahead.
Okay. Hi, Mauricio.
Hi.
My question is the following. What is the gain of M4, M4 with respect to G3 prime if are equivalents with respect to tautology preservation?
What is the gain, you say?
The gain, the benefits.
Okay, yeah. Thank you. Okay, well, we are following a kind of parallel approach to standard answer set programming. I have to say that answer set programming, the original has to do with so-called stable models using G3. But there are many people, there are researchers well known, Pereira, for instance, a group in Vienna, that suggested to have a stronger version of the stable semantics. And there have been several proposals. G3, using G3 prime, was one of them. Now, on the other hand, the stable model semantics has been also extended, so what it's called answer set programming, by allowing two kinds of negations. And for that purpose, they switch from G3 to certain Nelson logic. So in this parallel approach, we also propose to extend G3 prime in order to have two kinds of negations that seems to be very suitable for knowledge representation. However, as it happens in the stable model semantics with G3 and Nelson logic, we want to have to preserve exactly the same logic in terms of the one negation to the other one. So that means that we want a conservative extension. So what we want to have new is this new negation. And this new negation is going to behave very much as in the case of answer sets. Now, very recently, in answer set programming, they thought twice about Nelson logic. And for purpose of knowledge representation, that here is kind of more difficult to mention, they suggest certain switch and they propose a new logic. This is like, I don't know, one year ago, something like that. And we were doing exactly the same thing, and we need to change one of the axioms. So in this parallel view, we are now again close to the answer set programming, but in the original language, we are stronger in the sense that we are allowing to have more answers, more answer sets. This is again something that can be, I mean, this is not a definitive answer in the research, Some people claim that that's enough when what we have in answer sets. Others say that it's interesting to have this extension. As I mentioned, Pereira, other groups are proposing this extension, similar Vienna. And also it's interesting to even extend more and be able to allow certain kind of para-consistent behavior. Now, I want to have here a very concrete point. When you talk about para-consistent logics, there are different schools and different views. So we are following one that is kind of old, that is based in Jaskowski. And recently there is a paper by, I think, the Russian guy, Petrokhin, where in this Logical Universalis in 2018, where we are using this notion of para-consistent in the sense that certain formula is not a tautology, or is not, cannot be proved if you are using proof theory, which is alpha implies, not alpha implies beta. This is not so very standard. So some people, when they read our work, they get confused and they say, no, your logic is not para-consistent. Depends on the view. For certain views, it's not para-consistent, it's only para-complete. But for other less classical views, it's para-consistent. But it's completely para-consistent in the sense that we are interested in answer sets. And as far as we have this discussion with a group of answer sets also, it's enough to do it. But we haven't explored it. So this is like for future work, there is too much to do. There is a lot of things to do. But in the moment, the idea is to have an extension with this other negation and have this alternative for answer sets where we can have more answers, closer to classical in a way. I don't know if that helps you. Also, let me say something else, because I even with the question yesterday, since some people are have a experience with Prolog, and I mentioned here that generalizes Prolog, I have to say that there are like two lines also. One is very much like the standard kind of view of SAT solvers, where when you use a SAT solver, you want to have models, well, in some of these options, and a model is an answer. Similarly with answer sets, but also we have the style of Prolog, where you want to prove, so you have just a theory and you want to see if something is a consequence. So we have these two possibilities in answer set programming and in this other approach. But it's more common right now to consider these like multiple completions as like models. And these completions are very useful if you want to do diagnosis or planning or whatever. So what is a plan? You have your theory and you obtain these different completions that we can, in SAT solvers, you call it like models. And that's more like the view that we have here. But as I said before, we are going to have, in some cases, more answers than what you have in answer set, which I want to point out again. This is not better, not worse. This is another option. And some people are interested in these other options. Some people say, no, what we have in answer set is enough.
Thank you, Mauricio, for your answer.
Thank you very much.
Let me add something else. So quickly, just this is more like for Jesus, that is an expert in like using these theorem provers. And now it's very welcome also to be the possibility to have some like provers or something that we can use and perhaps take advantage of these provers for computing models in terms of logic programming. So there is also this, this is what I even had a discussion with Michael Gelfond, which is one of the founders of answer set programming. He said, well, all these approaches that have connections with logic, formal logic, are very interesting and have been to explore. And for instance, he was mentioned, it's very interesting to be able to prove some theorems in that will correspond to properties that we have in our theories that we are doing. And this is a topic that hasn't been explored enough. So theorem provers and things like that in these languages would be very useful as a way to have not just a solver, but a complete system that can do debugging, can obtain answers, can have properties in terms of theorems, and so on. So we are missing, I mean, on the people in logic programming, all like a very strong or complete infrastructure that could have many things that could help in many ways the programmer or the people that develop solutions in terms of these systems.
Yeah, I agree. Very interesting. Thank you, Mauricio.
Thank you very much, Master Osorio. We have another question. Go ahead, Vero.
Hi, good afternoon, Dr. Osorio.
Hi, Vero.
A question. How are you doing the completions? I mean, you have now two different negations. So these are weak completion, strong completions. They mix the negations. I mean, which is the way you construct your completions?
Okay, but that's a very important, very good point. That's a very good point, and I think it's important to mention, even starting with G3 prime, because we have here a switch with the standard stable semantics. In the stable semantics, we have a completions by means of one negation and two negations. But here, two negations implies the original formula, so it collapses. So we are using weak completions, and with weak completions, we had enough. Meanwhile, with the stable models, they use this strong completion. We have the negation of an atom and also the negation of the negation. Now we have to mix also, as you mentioned. We have to mix because we have to use the strong negation. We have literals in terms of an atom or the negation of the atom, but by negation we means the strong negations. And after this, we apply weak negation. That means we can add also another negation, the other one, to obtain them. We haven't published, we haven't written a paper about that. I wrote the software. As you know, I come more from computer science, and I am in some kind of strange mix of theory and practice. So in that way, I prefer first to develop the solver, even in a very rustic way. And so we have a very rustic software in order to play and to understand. But we haven't written a formalization of what we will call this, whatever, weak extensions for this logic. So we haven't done it, but I have programmed it, and that would be the style. But that was a very good point, because at least we have to make clear that our completions are not going to be exactly the ones that we're using in intuitionistic logic or this G3, G4, this chain of logics, because in that case it was very nice that the double negation doesn't imply the formula. Meanwhile, here it does. So in this case, we cannot use those ones. Thank you, Vero.
Thank you.
I couldn't see your talk. Sorry, I really had a problem, but I hope it's going to be online so that I can check it later, or you can send me to me, because I really wanted to see it. But
okay, it would be a pleasure.
Okay, thank you.
You're welcome.
Thank you very much. Any questions? Okay. Okay. We thank the speakers for your presentation. Well, we have 10 minutes to begin the next talk. We take this time to take a little break. The next talk is by Sophie Pachina. Pachina is correct, the last name? Thank you very much, Sophie.
By the way, can you hear me? Does it work? Okay, good, because I did not try. Yes, indeed, very well pronounced.
Oh, well,
Well
thank
done.
you. We take, Sophie, we take
Sure.
10 minutes, 10 minutes.
No problem.
Well.
Let's have a break. Okay, no problem.
Okay.
See you there.
Thanks. Hi there. Are you ready? Okay. The second talk by Luis Felipe Bartolo, unfortunately, was withdrawn. Then, to end this amazing event, I have the pleasure to introduce Sophie Pachina. Sophie is a full professor at University Rennes in the Department of Electrical Engineering and Computer Science. Her main research interests are logic, automata, and gains, imperfect information, synthesis problems, and model checking, among others. The name of this talk is Model Checking over Infinite Structures, Automatic Structures, and Regular Automatic Trees. Please go ahead, Sophie.
Thank you very much. I hope you hear me well. Is it
Very
okay?
well.
Okay, lovely. So good day, everybody. It's evening here in France. It's 36 degrees. So I took a look at Mexico, and I think it's cooler at your place, which is not usual. Okay, so thank you very much for this invitation, and I hope I will show you things that you don't know, which is always something interesting, but maybe you know a bit about it. Okay, so my research indeed is more on the, I would say, semantic side of logic. And I'm mainly interested in developing logics that help talking about the behavior of systems. So we have all sorts of models which look like relational structures one may find in classic logic, like first order or second order logic. And here I will discuss a bit how one can expect verifying properties of objects that are infinite, but that can obviously, in order to be given to some algorithm, which can be represented in a finite manner. And we will see how far we can go in the kind of properties we can prove if we stick to, I would say, yes, classical first order and monadic second order structures, logic, sorry. So this is the plan of my talk, so it's not very visible. I will straight on with motivation, but the idea is then to explain to you indeed where I want to go, and to recall the structures, the classical logics that will go fast, and then discuss the model checking problem over finite structure first, and then on infinite structures, and I will show you a result that we had about monadic second order logic over a pretty large class of structures. Okay. So this is the big picture. This big picture shows you some decidability frontier between model checking problem. So by model checking, I mean you have a class of models. Here on the left, the first column, you have finite structures, finite first order structures, and you take first order statement. And this is obviously decidable because you can exhaustively see if there exists an element such that for all and so on. So it might be costly, but at least it is feasible automatically by looking at the elements of this finite structure. Another thing which is also possible is to model check monadic second order logic, where for those who you all may know, monadic is only when you can quantify over sets of elements in the domain. So again, because the structure is finite, there are finitely many subsets of the domain, and you may develop a naive approach that guarantees decidability. And now in orange, I've put structures that are non-finite ones, but for which it is known that we can decide statements. So the first class of structures that are very, very nice ones are called automatic structures, where I will re-explain to you how one can verify a first order statement. And as you know, as you understand, as the domain is infinite potentially, quantifying universally over elements cannot be done in an exhaustive manner. Then we will kind of restrict the class of automatic structures and discuss regular trees, and we'll have MSO that can be decided on it. That's a very old classic result from Rabin 69. But as long as you equip your regular trees with a binary relation between nodes, which is just like the binary relation to be at equal level in the tree, then you lose decidability. So the idea was to kind of be able to restrict the logic, let's say, at this part here, to make it, let me see how I get my thing, to restrict this piece here into something weaker, but also somehow to enlarge. So this is weaker, but this is bigger. So I will show you objects that are regular automatic trees that contain the class of regular trees with the equal level predicate. So that's the picture I want to tell you about. Okay. So let me briefly recall what the relational structures are and our classical logic and the problems, the model checking problem I want to address. Okay. So start with structures. So you all know structures for classical logic. You have, for instance, so you have a domain and you have predicates of all kinds with certainty. Not noticeable, I mean, the remarkable structures are graphs with a set of vertices and a binary relation of edge, oriented or not. You also have those Kripke structures that sometimes people call transition systems for representing programs, execution of programs. So if it's Kripke structures, you have a set of states, set of initial states, and distinguished states or words. And you have a relation that sometimes have to do with agents and sometimes have to do with time progressing in transition systems. And you may decorate your states with atomic propositions. You also have very standard thing is the full binary tree, where the domain is given by the address in the tree. So you go left is 1, right is 2, and you go down the tree, and you may come here to the address 2, here 2 again, and 1, 2 to 1. And you can talk about two binary relations to say that this node is the left successor, one successor of the root here, or those two are related by sec1, while those two are related by sec2. And you have a unary predicate that tells you if you are in the root or not. So in general, a relational structure is given by domain, non-empty, and you have all sorts of relations of summarity over this domain. Okay, so particular objects that I'm interested in are trees. Trees where the domain in general, if I take here trees, let's say an n-ary tree, it means that you have a node has at most n successors. So the domain is the address. We've just seen the binary tree, so the case n equal 2. You have the root, sorry, here is a typo, which is a subset or can be seen as a unary predicate, which is a singleton, which is just the root, the empty address, the root of the tree. You have successors that tell you, given an address, you I take address U concatenated with G that gives you the successor. And you can add all sorts of relations between nodes as you like. So for example, you may put unary predicates, unary relations to color nodes. Green of X would hold if I replace X by node that is colored by green, sorry. And you may have this equal level predicate, which tells you that two nodes with these two addresses, they are at the same level if the addresses have the same length, because it means that you've made the same amount of steps going down the tree. So this is examples of extra binary relations you may put on trees. So this is what the binary tree looks like. You may indeed over-decorate it with equal level relation, which will relate those two, all the nodes at the same level would be related in a binary manner. So I have an implicit, I would say I can put dots, for instance, to differentiate. I have dots in between all arbitrary nodes at the same level. Okay, so now we take a look at the logic I'm interested in. So you have classically first order variables, which allows you to define your logic. So implicitly there is a fixed signature. So you have those, so it's a bit an abuse of notation, because I write with the same symbol what is in the signature of the language and its interpretation in the structure, but everybody understands what I mean. So you have atomic formulas here. You have all you need to have all the Boolean connectives, and you have quantification, and with negation, this existential quantification can be turned into universal one. So this is clear. So I will write this thing defined as, sorry, not exists x not phi. Well, not exists x not. Okay, so now we turn to MSO. So with MSO, you have extra variables called second order variables, and they're meant to describe sets. So you have standard atomic formulas that use first order variables. You can combine, you can use Boolean connectives. You can quantify over an element, and you have other kinds of atomic formulas that says that this element belongs to the set, and you may here have the second order quantification saying there exists a set such that. So we can have an alternative view of MSO where you only use second order variables, and you may have a statement saying that it is a singleton, so you quote an element. You have here inclusion between those that could be expressed here, meaning that for all x in capital X, if x is in capital X, then x is in capital Y, which corresponds to this. And you may only resort to second order quantification. And of course, implicitly, we will see that the interpretation of this formula holds only if for each second order variable, the fact that it is a singleton holds, but it's just, okay. And we classically have the notion of assignment. So an assignment tells you how to evaluate, how to interpret variables, both first order and second order in your structure. So first order variables will be mapped onto elements of the domain, while second order variable will be mapped onto subsets of the domain. And the classic notation is, given an assignment, I can tune it a bit to change the value of x to d, and same for second order variables. Do not hesitate to interrupt if needed. So because I want to write with my pen, I cannot use my next slide. I hope it doesn't disturb you. So if I take this tree, and if I want to say there is a way to color the entire tree with color green and red, such that immediate siblings have different colors, You would easily find that this is a way to write it. There are two sets. This, I'm sorry, I wrote it this way. I should have written it like this, but it's the same. Unary predicates. So I will freely, green of x is easier than x belongs to green. To green. It's a bit sloppy. So every node has to be colored. If a node is not colored by green, then it is colored by red and vice versa. And if you take two guys, and if it happens that they are friends, one is on the left, the other one is on the right, then they cannot have the same color. Something like that, okay? You may also write a formula that says that if you have the equal level predicate, say that all nodes of the same, of a given level are all colored the same and so on. So you can have a lot of properties, and regarding the relevance of this logic, well, it's a bit hidden, but we will see that typically with the additional relations when we put on the tree, we can, for instance, capture epistemic relations between histories of events along in the tree, and get back to dynamic epistemic logic, epistemic planning, and things like that. So the model checking problems are as expected. I take a finite description of a structure because I didn't tell you that this is a finite structure. And we will see how to instantiate this thing in order to have a well-stated problem. I take a formula, that's the FO model checking, and I want to know if the formula holds of this structure, and the same for MSO, okay? That's for a given class. So here the class will be written here. So that's the name of the two problems. Okay, so we go first to relational structure very briefly, just for you to have a kind of, I would say, references, bibliography about this. So actually, the big result comes from Stockmeyer, and was also studied by Vardy, where it's not only formulas of classical logic, but it's rather queries in databases. But it's more general. A query is you want to say a non-closed formula where you want to compute all the tuples of those three variables that make the formula true. So as we know already, LSP space complete. We're happy with it. As I said, it's not very surprising that it is decidable, but here is the exact complexity of the problem. So now if we turn to the input of your model checking, because we want to have algorithms, the input must be something finite. So in order to capture infinite structures, we will require to have a notion of finite presentation. So what we will consider are first a funny thing that I've just kind of made myself. It's not well known, but very convenient. Is the post-correspondence structures that I can first give as a set of dominoes, and I will explain how to derive a first-order structure, but that turn to be able to be presentable also with a finite set of finite state automata. I will explain. Then you have the classic automatic structures that really are, in essence, what can be represented by a finite set of finite state automata. But those finite state automata, well, just this, yes. And we're gonna build a strict subclass of automatic structures. What are those? That are those regular automatic trees that we exhibited with colleagues of mine, François Schwarzentrüber and Gaëtan Dueno-Tabo. It was a paper in AIML 2018. And I don't think I will have time to discuss other structures that are very well known. Dynamic epistemic logic structures, I don't know if you're familiar with them, but it is enough to give me those two objects, or an initial epistemic state and a finite action model that you can iterate, updating your model to reflect the information change in the initial epistemic state, and you may iterate forever, and you get an infinite structure of infinitely many epistemic states. And actually, there is a way to inject these objects in our class here, as long as we have some important hypothesis on the kind of action models we may use to generate this infinite structure. This is in the paper. Okay, so first of all, let me show you those funny post-correspondence structures. So are you all familiar with post-correspondence problem? Yes. So you have dominoes and you want to concatenate them in such a way that what I read, dominoes with two levels, the top and the bottom, with words, and you concatenate the dominoes and you read the word over this alphabet all along this concatenation, and you want to find a way to put dominoes. You may reuse the same domino several times, so that what is the sequence of letters that you get at the first level of the dominoes is equal to what you get at the bottom. So this is exactly what is said here. So this is known to be undecidable. Okay. And it's important because I will use this result to characterize the fact that I'm not able to verify first order logic on this class of structures. So the class of structures is obtained by all structures of this kind that you derive from any set of finite set of dominoes. So what is this structure? So first of all, the point of these structures are arbitrary words. Okay. Here we are. Now you have a unary predicate that tells you if your word is empty or not. And you have a binary relation that relates two words in your domain, as long as you can get the first one and the second one as respectively the first level or the second level of a concatenation of dominoes. They do not need to be the same. They are not the same in general, but I just put one domino, then another one, then another one, and I read what I have on the top, I read what I have on the bottom, and I consider that those two words, seen as elements of my domain, they are related by this relation, which is iteration of, related by a sequence of dominoes. Is it clear? Okay. So I show you here an example of how you may capture this structure with automata. So the domain first would be given by an automaton that's the initial state. It's a finite state, and you can execute your automaton while reading a word, and basically it accepts any word as long as it is over alphabet A and B. Starting from here, you may accept immediately, which allows you to accept the empty word also, which is part of the domain. Now I'm going to build one type automaton, which takes, you give me a word, and I'm going to tell you if it belongs to this unary predicate. Okay, fine. Here is the automaton. I read my word, and if this word is empty, I'm blocked here. It's not accepting, so basically it rejects the automaton in the language. It rejects epsilon, but it accepts any words as long as I have at least one letter, and then I reach this accepting state. So more funny here, and maybe you're less familiar with this, you may see this. This is a transducer. So it's a two-type automaton that eats two sequences, and it says that if I have an A here, and I have an AB here, it makes a move. So it reads this A and it comes here, and it reads this AB and it comes here, and it stays in his single state. So in order to accept this, for instance, I can have a word where I do this, then I do this again, then I do that. So it means that on the top I have A, B, and on the second tape I have AB, C. Okay? And as you may see here, very importantly, the two heads, they do not move at the same pace, okay, at the same time. So in general, these two-tape automata, they describe what people call rational relations, binary rational relations. Is it okay? Very simple tool. All right. So it can be shown that if I take a domino set, it's very easy to characterize the fact that there exists a way to put a finite sequence of domino with the same word on the top and at the bottom, if only if I should have, well, I put only R in my language, and R is interpreted here like that in my structure to say that there exists a word which is non-empty, because post you ask for non-emptiness, otherwise it is trivial. And so that by concatenating dominoes, this word is in relation with itself by the concatenation of dominoes. Okay, so it means that if I could model check first order logic over post correspondence structures, I would be able to decide a post correspondence problem, which is undecidable. So we get this as a corollary, and it's even worse on post correspondence structures. You cannot even model check this single formula. So input a structure, output, does it satisfy this? This you cannot decide. So let's come now to automatic structures. So they are very beautiful objects. So instead of having, well, I will still have this idea of two-tape automaton, but now I have a way to read the two tapes in a synchronized manner. That's the idea. So the two heads should move together at the same time. And thus, that allows to define relations that are a subclass of rational relations, but that are called regular relations, and can be captured by a finite state automaton with only one tape, which is a tape here, where now my alphabet is a product of letter here. So this is what I'm going to tell you. So consider the structure here that you know very well, which I've drawn here. And let me encode the structure. So I will design a structure that is isomorphic to this one. And first of all, I will encode very simply an integer in unary. So the encoding of n is a word over an alphabet, which is the alphabet I'm using for words is just one letter, it's letter 1. And I put 1, 1, 1, 1, 1, 1, 1 n times, and that encodes integer n. Now, I want to consider two words, and instead of considering them separately, I take here 1, 1, I take here 1, 1, 1, and now I read them like this. And because one may finish because the other one, I have an extra symbol, which is a blank. And this construction is called the convolution of the two words. When you take U convoluted with V, you just put them aligned. And for the one which is the smallest, if any, you complete the word with this square blank symbol. And now I can design an automaton, a standard one, no two tapes, just one tape, it reads one word, which accepts convolutions. So as it's written at the bottom, which accepts the convolution of two words if n is smaller than m. No, it's easy because, okay, I've changed my way of drawing automata because I should have written it this way, and now this arrow means final, okay, and they're square. Why? Because I couldn't manage to get my LaTeX here, my package automaton to be gentle with me today. So, but you can understand. So start tells you the initial state, and outgoing arrow tells you it's one of the finite states if there are several. So now give me a word that is the encoding of a pair of words by just the convolution. So as long as they are the same, I stay here. So in case it's the same word, it will be accepted, and indeed n is indeed less than equal to n. But if the first one ends with the second one, I'm perfectly happy. But I'm unhappy if the one is longer. Okay? So with this automaton, you can encode integers with words over alphabet 1 with the convention that n is a word of length n over this unique letter. And I have an automaton that perfectly captures those words where the first is corresponds, it encodes an integer which is less than equal the second one. Is it okay? So here is another example of an automatic structure. So you have a note with our address. I will use this very address as an encoding. So it means that I'm working on this alphabet. Okay. And now it's very easy to see that if I look at addresses, if I take two words, they are an address is related by successor one for another word. If this word is simply this address plus the new move to the left, which is 1. So now, is it easy to use an automaton that can recognize this binary relation between U and V? Yes. What do I expect? I expect the words to be exactly the same up to a point where I see that the second one, meaning V, has a 1, while U is ended. And all the rest is put to the bin, drop. Okay, so I can do the same one if I replace 1 by 2 and get just this automaton here, 2 to get for successor 2. I can even encode, I can capture with an automaton the equal level in simply that the two words are of the same length, meaning that if I convolute those two, I don't want any blank symbol, no for U, neither for U, nor for V. They must be of the same length, but they do not need to have the same. So I take two words, I read them like this. I want to finish the words at the same time, and here I don't care if the symbols are the same or not. I'm just concerned with the length. So I can read any pair of letters, synchronous letters, 1, 2, 2, 1, 1, 1, 2, 2, etc. So now I can give you a general definition of automatic structures. So you take a structure and you say that it is automatic if you can find first an automaton for the domain. So it means that you have an encoding function that takes an element of your domain, like an integer, and sends it to a word, okay? And your domain must be mapped onto, must be recognized with this encoding, must be recognized by a finite state automaton. Otherwise said, you have a way to encode the elements of your domain by a regular language. Okay, And on top of this, because you want also to capture automata for these relations of RET, let's say RI for generalities, you want an automaton that is able to accept convoluted words where, of course, each word corresponds to an element of the domain. So it encodes an element of the domain. And if I look at the very elements that are captured by this encoding, there are indeed legitimate tuples of this relation. Is it okay? So you have a way to look at your structure as a structure that is isomorphic to it, where the points are now words, finite words, and all the relations in your structure are now captured by finite state automata. So if I start with an automatic presentation like this, I have a very natural structure where the domain is this, the relation is this. I have a relation A1. This automaton is on some convolution, or it has a certain dimension alphabet. So you take this one, you add the blank, and you take the right arity of your relation. And this is how this automaton works. So it works over this alphabet. So it's tuples of letters here, A, B. And here you have Ri. And it encodes relation Ri that you had in your original structure. So what is cool, very cool, is that now I can address a very neat, clear, well-formed problem. I give you an automatic presentation. I give you first order formula, and I want to know if the underlying structure I can decide first order. So the answer is yes. And as you may understand, the domain, which is the language of this automaton, is in general infinite. But still, I can compute the truth value of any first order statement. So let me briefly explain how. So let me write, if I take a structure, this, if the formula has n free variables, I see phi as a relation, but n-ary relation. So it's the tuples, so that the formula holds when I replace, oops, sorry, I should put that. When I replace the variables by those values, so I see it as a relation. And now I show you how to compute the relation. So very importantly, the relation denoted by this formula is already given here. It's automaton AI. If I want, so this is given because my structure is automatic. So atomic formulas are already given by an automaton. If I want to negate, I complement the automaton corresponding to phi. If I want the conjunction, I intersect this automata. And there are finite state automata. It's perfectly, all this can be done. And if I want to abstract some variable in phi, well, I abstract my automaton was on 3 words, over 3 words that are read synchronously. And so U1, U2, U3. And if I want to say that there exists a way to find the third component, so that I simply take the automaton that now behaves like the previous one, but doesn't read the third component. And if it reaches a finite state, I know that I have a way to complete the third component, so that. So here is a very basic example. So here is a formula. So this one is given here. That's my structure. Now I project, this one has it's a 2-tape automaton, but synchronous with a convolution. So what I do is I simply remove the second component. and get this one. Now I want to compute this one. I take this one, I complement it, and I make sure that it will run over words that are elements of my domains. And I simply intersect the two automatons to get this. And it's very easy to see that the set of words that satisfy, so it's one word that satisfies this formula, is the word recognized by this automaton. Okay. So we know how to decide first order. So MSO is decidable over the full tree. Okay. This is cool. And what if I want to model check MSO over automatic structures? Well, it's very simple. It's hopeless because already the MSO theory of a particular automatic structure, so the tree with equal level predicates, is not decidable. So we cannot. So can we do something with a bit beyond first order and below MSO? So let me introduce you subclass of automatic structures. So in few words, very simply, you say that a tree, so I already consider a tree, and I say that it is regular automatic if I take the encoding of this big structure, which is my tree, the encoding is the identity, meaning that I want to know if with the addresses I am able, so this we've seen already that is easy to encode, because if I take an address V and I want to be the nth successor of U, then it's U.n. But I may have other relations here for which I would like to know if I have a finite state automaton that takes addresses of the nodes and is able to tell me with an automaton if those two are related by the relation, like equal level, for instance. I can do just by looking at the addresses and see if they have the same length, and then I know that they are at equal level. But you may have other relations that can be captured by a finite state automaton based on the encoding of the nodes as themselves, meaning as their address. Okay. So if you take such structures to understand how they are built, you can imagine that if I take an automatic tree here, the tree is obtained by unfolding some finite structure, a very gentle finite structure that you unfold as branches, okay, as a tree. And those relations can be seen as transversal relations in the tree. And those are very interesting objects because if you think of, for instance, epistemic reasoning, you can have two histories that are observed by a given agent. And the agent is not able to see what events have been performed, or maybe he can get confused with two events he cannot distinguish. If I turn back and I open my bag and I take something out, you don't see what I do. And it means that you know that I have opened my bag, but you don't know what's in there. Okay, so if I take this out, you don't know if I've taken out an object or another one. So some executional system might be indistinguishable to different agents. So this is what people call the epistemic relation for agent A. Sorry, I put an A because it's very standard, or maybe I. Ki means that the agent, if you take two histories, finite histories, and they are finite here and here, it might be the case that for him, those two are related by their indistinguishability, and one would say that an agent knows if for all possible related histories to a given one, something holds. So it's very important to be able to capture structures that are infinite trees, that's dynamic, and to have horizontal relations that correspond to, let's say, agent observations. So very importantly, I will not spend time because time flies. Here is on my slides, you may find an example of a tree, which is automatic. It's this tree, but for a very weird encoding, very, very weird encoding that is given here. So for example, if I take an address here, you see that the addresses are a certain amount of ones and another amount of two. And I decide to take as an encoding the word, which is, give me the binary version of integer I, binary encoding of j, and take the convolution. So this is a way of encoding this tree structure. And we can see that this tree indeed is encoded, but it's not encoded with its own addresses, because the language of addresses here is non-regular. But I may find another encoding so that the obtained thing here is regular. So it means that I have another way to encode the domain so that I have an automaton that perfectly describes all the nodes, but it's not the very encoding by the addresses. So some trees can be automatic, but not necessarily regular automatic trees, because the encoding used is not the very addresses. Okay. So with this encoding of addresses is very cool, because I have for free, okay, I have those ones already. As you know, V is the I successor of U if V is equal exactly to that, which can be checked by an automaton. But I have also suc star for free with an automaton. It's enough to check that V looks like U plus another word W, and I want U here, and I want to have symbols here. So it's the prefix, U is a prefix of V, meaning that in the address, V is down the tree along a branch after U. So with this encoding by addresses, we have for free many other predicates that come for free in the structure and are necessarily that can be described by regular automata. So I can add that in my first order signature for free, it will work. So this is said here, you can freely add many things in even less than equal, I mean, deeper in the tree and so on. So of course, this is decidable because rats are automatic structures, but MSO over rat is not, because as we saw the tree with equal level, its MSO theory is not decidable. So we have introduced chain MSO. So MSO, in general, you can quantify over any subset. So it means you take a tree, I haven't drawn a tree, you take a tree and you can quantify over arbitrary selection of nodes. Path MSO was already introduced long ago. It's you restrict the quantification of sets for sets that are full branches in the tree. So I can go fast, but it's easy to characterize a path in a structure in a tree T by saying that okay, one of the two is below along a branch, and it is connects. If two are in the path, then anyone in the middle is in the path as well. So if this one is in the path and this one is in the path, then this one must be in the path. It's a full branch. Okay, so you can use, this is path MSO as you could understand. This means there exists a path such that the tree satisfies the formula when variable X is replaced by this path. It's a powerful logic that captures temporal logics that quantify over paths, and very important in verification. There exists an execution, a long range for all executions, blah, blah, blah. And as I said, in trees that we unfold to represent programs, trees are execution of programs. So we have introduced something that generalizes path MSO, which is chain MSO. So a chain basically has a support, which is a path, but the chain is not the full path. It might be, you may remove certain nodes along that path. So it's more general than chain. A path is a chain, but the chain is not a path. Okay. So these are definitions. And you can express in chain MSO that something is a path. So I'll let you take a look, but I rephrase, I have a chain, and for all elements in that chain, if it has a successor, then there is a successor in that chain, meaning that you fill the chain, and it's not difficult. Okay, so what we have shown is that chain MSO is decidable, and I will briefly try to give you an idea of how the proof is conducted, but it might be a bit hard. Let me just see, because maybe I prefer to have questions. Well, I give you here an intuition of how I encode a chain, just the picture. So the chain is in blue, okay? The chain is in blue. So this chain has what I can call a support, which is a branch. So as the chain I consider is infinite, let's say that we can consider chains that are not non-finite, that are finite, sorry. But in case of I take an infinite chain, it has a support, which is the yellow one. And I'm going to encode this chain by taking its support, which is an infinite word. That's an infinite word. It means 2. I go left, then I go right, sorry, then I go left, right, and then I keep going left forever. So the yellow thing is infinite. Okay, so it's an infinite word. So instead of resorting to finite automata, we'll resort to the extension of finite automata to infinite words that are Buki automata, but they work pretty well. We can intersect, complement, things like that, and project. This is what we need for our logic. And I tell you, each time I go, so basically this is the support. I go down epsilon 2, 2, 1, 2, 1, 1, 2, 1, 2, etc. And the second component here tells me if this node along the support is in the chain or not. So 0 means it's not, and C epsilon is not colored blue, so it's not in the chain gamma. And so it's very easy, this encoding. And we can show that now we have an infinite word over like I can now read this word, if you like. How can I tell? I can read this word like this. So I say epsilon 0, 2, 1. So I follow my path. That's the intuition on the left. But now here I have a word, 1, 1, 2, etc. And sorry. No, it's not. Yes, it is. So here I read an infinite word that corresponds to following left, right, left, right, left, right. And I tell you which ones are in or not. So here I get a word over a very special alphabet that is this one, to the omega. And I can recognize chains, I can recognize tuple of chains, and I can build, for example, if I want to give me a chain, and I want to see if it encodes, if you give me something, I want to see if it can encode a chain that is just one point, a singleton. Well, I run the automaton that assume we know how to define a chain. On the left, it's a good word of the domain, and on the right, it's a 0 over 1. And here, the automaton that verifies that the second component of this encoding, I have a single occurrence of 1, which means that in here, there is only one place where I have 1. The rest is 0, which means that I have only a single node that is colored by blue. And there are all sorts of constructions like this. And at the end, what we get is that, I made it very long because, well, I meant to skip the proof actually, yeah. But so we can build an automaton. You give me the tree, you give me the formula you're interested in, and I can build a Buki automaton that tells me exactly if gamma is over n variables of chains. That tells me exactly how to recognize tuples of chains in my structure that satisfy this formula. So if my formula is closed, well, actually, if my formula is closed, the Buki automaton runs over a dimension of 0, which means that it is an automaton with no input alphabet, and it is enough to see if there is an execution of it while reading no words that leads to a finite state. So basically checking MSO over rational automatic trees amounts to checking the non-emptiness of a Buki automaton. But the Buki automaton, its construction is very costly because we complement and we project and we complement. And you know that each time you need to complement, there is a blow up with. Okay, so there are couples of corollaries with our results that I will skip, but old results saying that if the unary alphabet of your encoding, if you encode an automatic structure over a unary alphabet, then it is MSO is decidable. Well, this is because if you are on a unary alphabet, any subset is a chain. So you may simply, I mean, it means that when you say for all X, it means for all chain, and we know that over rational automatic trees, it is chain MSO is satisfiable. You can also have a lot of very rich logics. So I will try to conclude to let you understand how important it is. And of course, my slides will be available, and I will make them available. There are full proofs and constructions. But the idea is that, as I said, if I take an automatic tree here, you may understand the nodes as representing histories of something that happens. You may have effect of actions as the dynamics. So a history occurred, and you make an action, A, and you come to a new history, which basically is H point A. So the history is just the sequence of actions you have performed. This is very important in planning, for instance. Then you may decorate here things with atomic proposition, P holds, Q holds here, and so on, to have properties of the current situation, the current state. And you may have relation Ri that relate different histories, so that you may address, I mean, you may consider, as you know, because you say that Ki of some formula, if actually from a given history, is if only if for H prime, if they are related by this indistinguishability relation for agent I, then H prime satisfies also phi. Sorry for this for all, which is shouldn't be. It's a meta for all. So that's the semantic of knowing. It means that all histories that are indistinguishable to you also satisfy phi, so you're sure about phi. So here's the picture of how chain MSO goes far when you use this epistemic relations. And actually, with the decidability of chain MSO allows you to specify properties on epistemic problems for epistemic planning problems, where you may really use very powerful logics that have been used in the literature with very ad hoc proof for each of them. And this one, I'd say, is a hammer, because it's very, very easy to encode all the previous ones into chain MSO. So unfortunately, it's theoretical results, because the procedure we have that consists in building this automaton and check for non-emptiness yields a non-elementary procedure. It is Kx time with the number of block alternations between existential and full quantification. And there is indeed in this paper, and also in a recent survey we did on epistemic planning, a clear link between dynamic epistemic logic and epistemic planning and rational automatic trees. Voilà, so I hope, so you also have the bibliography I mentioned. So I hope you had a journey in this very powerful way of encoding infinite structure into finite ones, and to tightly connect formulas with automata. And I'm ready to answer your questions.
Okay, thanks, Sophie. Your talk was interesting. Model checking and automata are not my area, but your talk was interesting. I wish to learn in some moment of my life this topic. Thank you, Sophie.
Thank you very much for listening.
We are in time. We have a few minutes for do any questions. Guys, any questions? Okay, Everardo, please go ahead.
Okay, thank you. Thank you. First of all, thank you for accepting to give the talk, Sophie. Well, my question is regarding the results you showed. For instance, the last one about the complexity. All those desirability results were exclusively for model checking, or are we talking also for validity, satisfiability?
So there is very little hope to do something better than, but already FO is a problem. No? So I mean, I don't know much what to answer, but FO is already a problem for finite structures. I mean, with the Trachtenbrot theorem that tells you that you cannot decide validity of FO over the class of finite structures. So it's like, this is why we turn to model checking. And I mean, in the community I'm in, we want to reason on a particular object which corresponds indeed to I would say a computing system, or well, on my side, I'm much more now involved in multi-agent systems where agents communicate and have only partial information, or in games where you look for coalitions that choose actions against the others, or even open systems with an environment and should be robust. So it's about synthesizing synthesizing a subset of your computation tree, so controlling the system so that something holds, things like that. So MSO is very important to be able to select a subpart of the tree, because if you can compute this subpart, it means that you know what to forbid in your system to execute, so that it keeps safe, or it guarantees some property along all its executions and so on. So I would say that yes, at least regarding classical logic, I mean, because of FO is already so hopeless, even on finite structures. I mean, I don't think it's worth trying anything.
Okay, thank you very much.
Thank you, Everardo. Fabio, go ahead, please.
Hi, thank you very much for the nice talk, for the overview of this state-of-the-art results. Just out of curiosity, can you say something about if there are similar treatments or research when dealing with tree automata or Buche automata, and also what about the role of games in the theory, in the research?
Okay, so when you take MSO in its full generality, and you stick to structures that are trees, again. Trees, as you could understand, are very important because they correspond to computation trees. I mean, that's why. So if you take or a game arena, which is finite, but you look at all the plays, and the plays are those paths along the tree. They are infinite horizon games, I mean. So what we are able to do is to associate to any MSO formula that tells about trees. So you have successor left, right, and so on. And you may also have unranked trees that are considered. So you don't have a finite branching degree. You can associate to any MSO formula a tree automaton. So those beasts are beautiful objects. And you may also have infinite tree automata. So inputs are infinite trees. No, not input, I shouldn't say that. They denote a set of infinite trees. That's what they denote. Just as if you take a Buche automaton, it denotes a set of infinite words. Obviously, you're not going to give me the input and see if the run is accepting. So it's just a way to denote infinite objects or sets of infinite objects. So you have the ability to compute for each MSO formula an automaton, which is an infinite tree automaton that characterizes those trees that satisfy the formula. Okay, and with those tree automata, you may feed the automaton. You may ask the model checking problem where the input is not an infinite tree. I have to find a way to finitely represent it. So you may represent your infinite tree by give me a regular one, which can be folded back into a finite state system. And with this finite state system that represents your infinite tree and your tree automaton, those are two finite objects. You may, by a product, build a two-player game with some infinitary conditions, so that the first player, often called Eve, and the other one is called Adam. Eve has a finite as a winning strategy, if only if the tree belongs to the language of the automaton. So that's the first way you can see games in this picture. And And for MSO, you would need infinite tree automata with accepting conditions that are, because it's infinite objects, that are a kind of generalization of Buki conditions of visiting infinitely often and accepting state when you read an infinite word. It's called parity condition, and it's very powerful. So that's where you can see games mainly. Now, just to finish and not to take you all too long, there is another dimension for games where you take an arena, even a multiplayer arena, okay, turn-based games, say, or at least games given in extensive manner. And the player may play simultaneously in one step, each one chooses something, or they play in turn. That's a degenerated case of the concurrent games. So you take a big arena, finite, with positions, moves, where a move is a vector of actions chosen by, or move chosen by individually by players. And for instance, and of course, those positions in the game are decorated by some properties, as if that was a property of a state of some programs. So you put atomic propositions there, and you can say, if I have 3 players, do the first 2 players have a strategy against the third one, so that all the outcomes satisfy a given, I don't know, CTL star formula. Like infinitely often Q if implies infinitely often P. And so infinitely often is very important in programs because it had to do with fairness in programs. Systems fairness is if I ask to print infinitely often, then it will be printed infinitely often, or request infinitely often, granted infinitely often, something like that. So infinitely often is very important in our setting. So here you have games, and there is a way to develop strategic reasoning logics. Say that, is it the case that there is such a strategy for those, so that whatever the other does, they come to a point where now there is a strategy of the first one and the third one, so that blah, 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 etc. And those logics can be model checked. It quantifies our strategies, which may necessarily be memoryless, so you may take into account the entire history and so on. They can be model checked over the arena by associating to this formula that quantifies our strategy, we can associate a tree automaton again and check for non-emptiness to model check. So what I mean is that for those people who are interested not in abstract reasoning for validities and things like that, but interested in model checking, I think now you can hardly do it without this wonderful tool in its full generality that is that are automata. And by automata, I also mean 2 tapes, 3 tapes, K tapes, transducers, and so on. And automata can also be equipped with a stack, so push down automata and things like that. So you have a big literature that basically you resort to automata to model check even very, very powerful, very expressive logic regarding strategic reasoning in multi-agent systems.
Thank you very much. Thank you.
You're welcome.
Thank you, Sophie. Your talk was fascinating. Any questions? Another questions? No?
Well, I think I've said everything, no? Anyway, I was very happy to join you because, yes, happy to be a bit part of me over there with you. And I also appreciated I couldn't attend all the talks, but really I learn a lot, and I'm really, even though it's not my field. Well, I'm not a pure logician, let's say. I'm very, very sensitive and very, very touched by all those questions of reasoning on which laws can be defined so that the entire thing works well, and proof theory is also very fascinating, I must admit, and it's our friend. I mean, we try to model check and people try to prove, so it's complementary, and I find all this very, very fascinating. So, and you seem to be really big experts. I'm very impressed. It's cool.
Thanks, Sophie. We thank the speaker for her participations.
I thank everyone. Okay, so yes.
Well, we're glad to end this event and say see you the next year. Thanks to all participants, committees, and talkers and organizers, of course. Everardo, Fabio, Lourdes, do you want to say something to end this event?
Well, maybe only to say thanks to all of you again, and we hope to see you soon in another place. And of course, there will be a further communication about the certificates of participation and the publications, but that will be later. Now we take some days to rest, please.
Everardo, please.
Yeah, I also want to thank everybody, because well, this workshop is for all of you, and we are very happy to be able to contribute. And also, I would like to thank the invited speakers. They all were very good talks and interesting talks. And that's it. So thank you all. See you soon, as Fabio said.
Thank you, Everardo. Lourdes, please.
Yes, so thank you. Merci beaucoup, Sophie. This was a very interesting talk. And as I said yesterday, this workshop and all the collaborations here are intended to open doors, to connect people, to make some new links, to collaborate, not just in Mexico, not just in Latin America, but with other people that share our interests and our topics of research. Thank you again, and see you soon, hopefully in person. And thanks again for all people here.
So bye-bye, everyone.
Thanks.
Take care. Bye-bye.
Thank you. Bye-bye.
Gracias. Seguimos en contacto. Nos vemos.
Nos vemos,
Nos vemos,
maestro Valle.
Gracias.
Gracias.
Saludos de Ale también para ustedes. Hasta luego.
Pásala bien.
Gracias.
Pásala bien todos. Nos vemos.
Gracias.
Nos vemos.